high use in the neighborhood. So
on the shore I stand alone. Ocean's whisper calls my name. Depth and longing in my soul, seeking more than just this game. Waves crash softly at my feet, echoes in my heart so deep. Eyes on horizon far and true, longing for a love so steep. Deep calls to deep inside of me, where the sky meets endless sea. Heartbeats blend with ocean's roar, seeking depth I can't ignore. Echoes in my heart so deep, eyes on horizon far and true, longing for a love so steep. Deep calls to deep inside of me, where the sky meets endless sea. Heartbeats blend with ocean's roar, seeking depth I can't ignore. Shells and sand beneath my toes, tides reveal what ebb and flows. In the quiet still I hear whisper longings crystal clear. Deep calls to deep inside of me, where the sky meets endless sea. Heartbeats blend with ocean's roar, seeking depth I can't ignore. Desire, burning with a holy fire. Depth of love beyond all dreams, in the vastness it redeems. Deep calls to deep inside of me, where the sky meets endless sea. Heartbeats blend with ocean's roar, seeking depth I can't ignore.
hey everybody, welcome to When Deep Calls Deep. And I say this every time, but every time it's true too. I'm so excited about this episode because they're all fun and they're all good, but this is a little bit different from what we kind of normally do around here. And the last one we did with Ronnie and Shaun was spectacular, and I got a lot of really positive feedback about it. And so I was like, well, we got to get the band together again and do this again because that was so fantastic. And I'm still it's still in my top favorite of my episodes that we've done. Like I had so much fun doing it, and the space stuff was awesome. So it just, yeah, I'm really, really excited about this and really looking forward to this. So let's start out with, how is everybody? Shaun, how are you? It's been a little while since we've seen you around here.
Yeah, it's been a while since I've been on here, but I'm glad to be back, and I'm so happy to be on here with Ronnie because I love space stuff. I love all of the stuff that he gets to teach us. I try so hard to follow all of the stuff that he's showing, but I feel like his brain works just so fast, and I'm trying to keep up. But I love it, and I love being able to see the amount of work and know-how that goes into just producing the kinds of stuff that we take for granted on Google Images, and it's just so awesome, and it's such a blessing to be able to see somebody like Ronnie who comes and brings us this information and this expertise. So I'm happy to be here, and I'm happy to be here with Ronnie.
Oh, I think Shaun's just frozen again there.
Oh no,
Everybody's having
yeah, I'm glad to be here too because I got good rapport with both of you guys. Didn't know Shaun before. Shaun's a cool cat, so I'm a happy camper today.
yeah, this is one of the funnest things for me about doing a channel and doing YouTube is meeting so many fun and spectacular people. Like
Hmm.
I would, I'm just having a great time. So Ronnie, welcome back to When Deep Calls Deep. How are you doing, friend?
Oh, I'm great. I'm great now that I found my turtle on the floor behind my desk in the corner, looking at me all innocent, like as if she didn't just jump out of the tank and spend the night on the floor. But she's good. And I'm good too, yeah. So as you know, one of the delays that I encountered before your show was having to look for my turtle. I go to feed my two turtles, and one of them isn't in the tank, and I'm like, "Where is Squirtle, the other one?" And she was not in the tank, but we found her, so it's all good. And she did not look any worse for the wear. Some of my turtles they come out of the tank, they bump into something. You got to worry. One time, I think my turtle her eye wouldn't open. And I found out it was just dry, so like I got all panicky, bought some antibiotics, and then right before I put it back in the tank, she's fine. So I'm like, all right, cool. At least I don't have to use any medication on you that I'm not sure is safe. But yeah, and other than that, we got some I'm glad you gave me some cool info. You got some topics you mentioned earlier. So I may not be an expert on the butterfly nebula, but I think in some of the stuff I was reading, I may be able to share some insight on that because sometimes when you're reading these things, there's a lot of these hand wave terms that don't really mean anything on their own. So I think I may be able to bridge the gap there.
Okay, I think I had to shut some stuff down. My internet's been really laggy. It's that time of day because I live in a very crowded subdivision
Mm-hmm.
where everybody's like online, and so even though we have screaming fast, um, not we have the I don't even know what it's called now. My brain just is shutting down. Anyway, we have really screaming fast fiber internet, but
Ah,
because the neighborhood, this is the time of day when this kind of gets overloaded on the whole system, so it's lagging a little bit. So I tried to shut down as much as I could on my stuff to lessen the load on my computer, at least anyway. So if it's laggy, my apologies. I have a neighborhood problem, so
so far so
we
good.
do we do the best we can. So I am really so I sent Ronnie because I had a couple of people when from the last time we did ask about a couple things. So I sent those to him earlier about looking at the butterfly nebula and looking at Orion's belt because there was some questions. Actually, I do need to open that browser because I need to see what those questions were because I don't remember off the top of my head. Oops, not that one. This one. So we're talking about the Butterfly Nebula, and somebody asked her in Orion's belt. So I asked Ronnie if there was a way to look at those because I don't really know what those are either. I'm not um, really versed in space type stuff. I just think it's really really cool, and Ronnie's showing us some pretty amazing stuff that I've never seen before. So um, that's kind of where I asked him to start. So at this point, I'm just going to step back and I'm going to hand things over to Ronnie, and you just start us out wherever you want to go with those. And Sean and I will just sit back and be amazed and ask questions as they come up. So,
Well, yeah, I'll be happy to get us started here. Since you mentioned the Butterfly Nebula and Orion's Belt, I actually took a little bit of time going into my backyard PC to retrieve, if I had any recent images because I recently recaptured pictures of the Orion Nebula, and I didn't process them yet, but maybe we can share a little bit of that workflow and just see what a raw image of the Orion Nebula looks like, and then from there we could take a look at what it would look like in a couple of apps because I have two apps just like the one we used last time, but we have another one that I didn't even show you guys that's pretty interesting, and it's got a pretty interesting backstory of that application. So real quick, I'm just pulling up an image on my backyard PC right now because if we look at the shared screen area here, let's see here. Yeah, I don't know if you want to pop that onto the screen. I think it's already sharing on the bottom of there. It's got the add to stream button right next to my face, so like next to the bottom left corner. Um, but let's see here. Either that, I could also hit this button too. So whichever way it works. Because I don't need full screen yet. So I don't even need full screen for this part here. So basically this is where I store the images, where I take the pictures. Whenever I set the telescope up at nighttime, and in this folder it'll tell me what settings I used on the camera. And this is the Orion Nebula. And the reason I want to recapture the Orion Nebula is because last time I captured it, I did it on a telescope that has too much zoom, which is not really a problem. But, when you're doing a nebula, you want to get a nice wide shot. And this is like a pretty raw image right here. You can see it's pretty cool on its own, but no color yet, right? And this one here, we did it in the hydrogen filter. So this is all really just shades of ruby red. So if I really wanted to, I guess I could make it look red, although I don't think it would be a natural or accurate red. But there is a button that will make it look red if we want to just kind of apply that. Oops, whoa, what did I just do? Okay, that's not what. Okay, a lot of funny features in this app, by the
Wow.
way. It does all kinds of. This is the app that
That
is used by
was
the
cool.
hardcore guys. Like I don't know, I don't even know what that does, but it's got all these weird features like photometry and astrometry. So photometry, I think you're measuring like the brightness of stars, and you're doing some like. In fact, let's get out of that before I get us lost. But where's the color filter thingamajig? Here we go. View color mode, Cinnabar. So that's close enough. So like I said, but mainly
Wow.
what I might do in this app is when I take a raw image, I'm using this app mainly just to preview it, to check it out, see like what is it going to look like when when I actually get around to processing it. So as we discussed last time, we usually stack these, but just by playing with the histogram, and that's what we're doing up here. This is the histogram adjustment. Sometimes you want to stretch the histogram, so you're either trying to crank out more detail, so you might crank it out so we get more of that outer edge area, or in this case, the Orion Nebula is so bright that sometimes the challenge is getting this area not to blow out in the middle here. So this one's, I didn't process yet because I was still trying to collect a little more data, but I think the season is almost over for this object. So with the season coming to an end, for where I can easily capture this object, I'll just work with whatever images I have. But this time around, I'm looking forward to getting this because I did it separate images using a shorter exposure time in the center there. And it's my hope that I can combine the bright image that we're seeing here with the less bright image and get like just more texture, more shades of red into there. And let's just do a quick experiment before we'll go on to some little more interesting view here. But for fun, we're gonna just do a little science. No, I'm kidding. But joke aside, we're gonna do a little. Not science, but we're gonna do the basic processing. So we already got our raw images in the hydrogen filter, but these were done at 15 seconds. I'm sorry, 600 seconds. That's 10 minutes at a temperature of 15 degrees Celsius. So I have these dark images here, and these are the ones that you use for subtracting out the hot pixels or any, imperfections in the image sensor. And so, where's the date on these? I want to make sure I use the newest one. They're about the same age. Okay, so let's just open up a random one and see what it looks like. Okay, so that's what the camera sees when you don't have any lens cap on it. That's called amp glow. That's just the nature of how a CMOS image sensor works. But mainly what we want is the more minutes, the longer the exposure time that we're running, the more of these white dots we're going to get. And these are not stars. And so, in this image here, we don't see too many of them in this, let's see, automatic stretch. We do see a few of them. So we see stars, they're like the round-shaped ones. And then anything that's a perfect square, like this guy right here, is not a star. And so by taking a picture of a blank image sensor, the software can subtract out those squares because it now knows what belongs there and what's from the actual object. So what we would do is we would take that dark frame and apply it to this stack. We told the program that this is a dark frame, and then we would say, hey, let's register these, and it's going to do something called registration, where it kind of just analyzes the images, checks how if they're different and other things that I couldn't even imagine, and then it gives me an error message. Oh, okay, that's weird. Maybe the weather was bad that night. So what it just told me was only one frame will be stacked. And so these are the things that you'll encounter sometimes, and let's see if we can find out why. Oh, I see why. Yes, I bet you the sun was rising that point in time. What
Well,
time were these
even
taken? Well, I'm just curious either way, but I'm going to show you something else now. But I was just curious to see how that would go. Oh, yeah, these are blurry. Look at
yeah,
that. Yeah, so
but
this
even
is
just yeah.
knocking it out of the park over here with the picture
But
here.
even
But yeah,
just
so
that with the and just what you
I
showed us with that red on there was just amazing.
Oh, well, it is pretty cool. I gotta say, first time I did that, like, even though, like, these are not images you would go to the astronomy
Hmm.
forum, you wouldn't go to a community with, like, a bunch of astronomy people and be like, look what I took, a single black and white frame of this object. But it is, like, especially the first time I seen it, it's like versus seeing nothing versus not having an actual picture stored on your computer. It's like really cool on its own. And yeah, like half the time I find that to be plenty of fun. But I'll admit some of the hardcore nerds would not be as impressed. They'd be like, okay, well now where's the final image? But that's a learning process on its own. I gotta say, like this AI stuff. One thing I like about it is like um, I remember I was watching an old TV show called Computer Chronicles, and it was like 80s computers, and it went on until the late 90s basically. And it was actually one of the pioneers of computing was on that show. One of the pioneers of PC computing was on that show, I should say. And they would just kind of review things. They would have people on for interviews, but in the 80s especially, like things were coming out rapidly, and this is like PCs were a new thing, so like every time something new came out that you could do on your own home PC or in an office, it was a big deal because you no longer needed to have like a large data center to like do basic stuff. And one of the things they talked about were called expert systems. Like if you were it's called an expert system or a decision support system. So like if you're on an oil rig and the oil drill gets stuck, instead of like calling an engineer to come out, maybe you can't make a long distance phone call from the oil rig back in the 1980s. So instead, you go to a computer, you type in, this is the problem I'm having. And then the computer would respond like based on like very simple logic, but like the early form of AI in that it's using basic reasoning. And it would ask you like, well, did you check if this is if the hydraulics are on? Did you check this? Could it be that this is stuck? Find out if this part is stuck and then return, and you come back to the computer and say, yes, the bearing was rusty or whatever it is, and the computer would then give you further instructions like what the worker would fix or what at what point he needs someone to come out and actually do a real repair job. And so the theory behind that was the oil company spends money on this software so they don't have to waste money on like house calls that are unnecessary when you got to send a guy in via helicopter or boat. So the reason I mentioned that is because when you're using AI, it's a lot similar. Like you're having a conversation with something that has slightly better reasoning, like so significantly better reasoning skill because it's trained on, depending on which AI you're using. If you're using Grok, it trained on stuff that people say. So it's not really the highest accuracy, but like sometimes that could be really handy on certain things, and other times I noticed that if you have the paid ChatGPT account, like in fact when we like we should definitely talk in greater detail on Butterfly Nebula in a little bit, but for now, I'll just give you a little bit of a preview of how I used this to answer two questions. So I was under the misunderstanding that the Butterfly Nebula was a quasar. Apparently it's not, but this is an oversimplified thing. I'm almost using it like Google in this context. But what I found was interesting was Amber's question was, is the what was the is the are the stars of the Pleiades nebula? Pleiades is weird. It's like a star cluster. It's like a nebula, but it is a nebula. So anyway, are the stars of the Pleiades nebula gravitationally locked stars? Now, to be honest, I didn't know what that meant in the context, but I know we often think about the term tidally locked when we're thinking about this stuff, and I should definitely pull up that app just in a moment so we have it handy. There we go. I'm going to let that application load up because I think it's going to give us some really relevant examples here. But anyway, the answer to your question, Amber, is as follows, and I'll interpret it as we go along. Great question. The Pleiades is also known as the Seven Sisters. It is an open star cluster located in the constellation Taurus. So, see, that's why I get confused. It is a star cluster, but it is also a nebula. You got gas floating around in there. It's got that dirty windshield look. Like, I swear, a picture of the Pleiades, like, especially when you just, like, unprocessed, when it's unprocessed, looks like a dirty windshield. It looks like, when you have, like in the morning when the sun is hitting it at an angle, and yeah, it looks kind of like that. It contains several hundred stars, although nobody ever talks about anyone but the seven. But jokes aside, hundreds of stars, though the brightest ones typically 6 to 9. See, that's why I get confused. You know how many times I sat down counting the stars of the Pleiades, and I'm like, I'm coming up with too many? I guess maybe that's because in the old days you can only see seven with your own eyes or something like that. Before you had all the wide aperture telescopes and the aperture, how wide your aperture is, uh, dictates your light gathering ability. And so that's why, whether you're using a telescope or astronomical binoculars, you see more using a telescope. Sometimes the name of the game isn't about zooming in on something, it's simply about just getting increased light gathering power. And that's why there's often emphasis on doing the astronomy hobby, whether it be photography or simply viewing. But in my opinion, when it comes to looking at the stars visually, it becomes especially important to have like less light pollution, because like I remember when I visited my brother upstate, I could see the Milky Way like with my own eyes. Like I could see like the stars lining up in that straight. I think we did. I show that last time. Do you guys remember if I showed? I might not have. Okay, well I'll pull that up because that was a cool one, and it was really cool because like I didn't do anything. I just used my phone, and the only thing I regret, which is not really a real strong regret, but the only regret I have about that is I wish I put the camera into pro camera mode. Because Samsung phones have like a lot of different operating modes for the camera, including like how you can operate it like a old school SLR camera where you put it into a manual mode. So I did that. I kept it simple, but I did do that. I did like whatever exposure time it allowed me to do, which was maybe like 2 minutes. And I was already able to see a lot of stars in the sky. There we go. I'm just scrolling down, scrolling down. Oh, that's cute. A picture of my tortoise. Okay, there we're going to scroll down a lot more. Okay, there we go. Okay, let's click on the post. Make sure it loads. All right, good. Full screen mode. Boom. Alrighty. And let's see. I could even maybe, let me try something out real quick. Okay. What screen number was that? Number 3? I think it was number 3. Yeah. Okay. There we go. Oops. Okay. Well, anyway, so there we go. So for now, we got this picture right here. And yeah, so I used the pro mode. Okay, so I did use the pro mode. So in the Samsung camera app, there's a button on the bottom right above the picture button or the record button that says more. And when you click on more, you get a number of other options, including pro mode. And they got pro mode for video and still photography. And basically, it gives you manual control like an SLR camera. And although today, when you see an SLR camera, people tend to use them in an automatic mode. There was a time where SLR cameras were nothing but manually operated. Like you did everything. You adjusted your focus, you adjusted your aperture, which is limiting the light going through the lens, but it also controls how much of an area is in or out of focus. So if you have a wide aperture, it lets in more light, but the consequence of that is only my face will be in focus. And interestingly, the telescopes we use, they only have one aperture setting, so they're on the widest aperture, so that's why it's critical you get it in focus. But on an SLR camera, if you shrink the aperture, let's say you have a lot of light, and all of your other settings allow for it, you got the right type of film, then a smaller aperture makes it easier, because even though it's not autofocus, you can essentially focus within a ballpark. So if you focus on my nose, everything from here to here will be in focus. And so if you know your subject is going to be in that general, at that distance, maybe you're photographing a track meet or something like that. Maybe someone's, doing a pole vault, some kind of Olympic sport, and you're at that finish line trying to get that, $10,000 photograph. That's gonna, make it easier, because now you're not gonna have to tweak the focus as the runner is passing the finish line. You just know you're already gonna be in focus, whether it's the guy on the closest to the camera or the furthest from the camera. It's gonna be in focus, and so you get that quick snapshot. But the reason I bring up all of that is that's the purpose of having these manual controls. You got the focus, you got the aperture, which controls brightness, and depth of field, which is what I was just describing when something's, when you got a range of focus. And then you got your shutter speed. And logically, a faster shutter speed can freeze things. So if I'm like flapping my hands like an angel, a slow shutter speed is going to give you a lot of motion blur. But at the same time, a fast shutter speed is going to get let in less light. Because the whole point of having the shutter open is to let that film or that sensor soak in the photons, soak in the light. Whatever light is, the longer the shutter is open, the more light you're collecting. So while doing normal indoor photography, or while using a flash. You can use a faster shutter speed when using a flash. When you're not using a flash and you're indoors, your camera is going to automatically use a slower shutter speed. Or in the case of a hardcore photography nerd or someone back in the 1960s, you're going to pick a slower shutter speed manually in order to compensate for the fact that you don't have a flash. And then, of course, conversely, when you're outside, it's really bright out, so you can get away with using a faster shutter speed. So, in the case of me being in Connecticut or on the border of upstate New York and Connecticut, I'd say like literally like on the eastern side of New York State, but about 50% up on Connecticut. So like halfway from the bottom of Connecticut to the top of Connecticut. That's the part of New York State I was at. And all I did was I set the camera to pro mode using 30-second exposures, ISO 3200, which is just saying like when you remember the 90s, you bought Kodak 100 film or Kodak 400 film. So this is like, like about 4 times faster than say Kodak 800 film. And in fact, I did ISO 3200 and 1600 because the higher the ISO, the more grainy the image gets. And that's similar to why earlier when I showed you the dark exposure, that picture where it had all the white dots, that was essentially due to the gain setting, which is very similar to ISO. The higher the gain, the higher the ISO, the more of that stuff you're going to pick up. So I managed that by using 1600. Basically, I was just seeing what worked, and I was surprised. Like, I mean, I kind of knew I was going to get something, but I was surprised I was able to get it to work as decently well as it did. And although this may not be much to see, let me just make sure I got this organized here. Okay, cool. There we go. You got like this picture here. You can see it's a little bit, the star's a little bit oblong, but the part that jumps out at me is, oh wow, a shooting star. I just noticed that. It's like a little line right over there. It might be an airplane, might be a meteorite, but you can definitely see like that this area is darker. And we're going to see as we go along. This is just the first image I showed you so far. So we'll go to image number 2. And now we're seeing a little bit more. And you can see here how, once again, we got this darker thing going diagonally across our screen. And then, let's see, we're going to get the next image. Okay, that one here, we don't see much in there, but we're going to keep rolling. I'm going to open these in new browser tabs so we can kind of just see them all. Okay, so once again, a little dark spot in the bottom right corner. Looks like I see a couple leaves from a tree up here. And then this one here, we are getting progress. So now you can see like this tall like thing here. I feel like these pictures are cropped. I might have cropped these for posting on YouTube. And then in one of these images, I'm kind of hoping to see, I was hoping to show you guys Andromeda, but not a big deal. It just looks like a little oval. But the point is that, yeah, the darker the sky, you can actually see this. And, where I live like in one of the 5 boroughs of New York City. I believe it's the term, I don't know if I'm pronouncing it right, but it's called a Bortle 8 sky. So let's see if we got like, well, that's spelled correctly. It's got to be, I guess, named after some scientist named Bortle. And in this picture here, I'd say that, so the lower the number, the better. So I might have been in a Bortle 2 or 3. I was probably in a Bortle 3 sky, I would have to guess. But you can see in this graphic here, that's pretty favorable. Like, whereas if you go to the deserts of Chile, you're going to be dealing with a Bortle 1 sky. So your eyes will adjust to that sky a little bit better, and you'll see that much more. But Bortle 3 is like quite stupendous. I mean, like quite satisfactory, I would argue. Whereas I'm living in a 7 or 8, which in this picture you can see like an 8 is like just like there's nothing there. And I'm in a number 7. It's weird. So I'm technically in an 8, but I would argue I'm in a 7 because like I definitely see it's weird. Like, it depends on the time of the year, depends on the humidity, but like I'm kind of in that 7 or 8 area. I'm not quite a 9. One thing I noticed was like if I'm standing in a parking lot with bright lights, I certainly see almost nothing, but sometimes I'll see Jupiter, like, and then if I am in the back of that same supermarket, I'll see a little bit more. So of course there's a function of how much your eyes adjust. But yeah, in that part of upstate New York versus my area, if I did the same thing with my camera phone, in fact, how did I use my camera phone? I know I described the settings. There we go. So I know I described the settings, but I didn't tell you how I operated the camera. So what I did was I put the camera on like a delay timer, like I don't know, like maybe like a 5 second delay or something like that. And oh, that's cool. I can share my screen and be on camera. Okay, I'll do it like that. Cool, that works. Thanks, Amber. So basically, I put the camera on like a 5 second timer. I hit the shutter release button. I put the camera on the ground, camera facing up like that. Just laid it on the ground flat. Walked away. Waited. I heard a clicking sound in my headphones. I don't know. I guess it's just a quirk of the way the camera works. So that kind of helped me to know when to pick up the camera because otherwise I'd probably wait an extra 10 seconds and, in the cold, that could, get annoying. But anyway, yeah. And I did that multiple times. And sometimes the camera would shift a little bit. Sometimes it would slide across the ground because you have gravel on the ground, like little rocks. It was like in my brother's driveway, basically. And after the fact, somebody told me that I could have used the pen on my phone. Apparently, the Galaxy Note series phones, if you press the button on the pen, it acts like a remote shutter release. So yeah, if you ever need to do selfies or you're doing a group photo or something like that, you put the camera on a tripod. That might be worth doing. By the way, are you guys on mute or is my sound not working?
Yeah, no,
I'm on a manual mute.
Okay, good.
Yeah.
I just want to make sure. Okay, I was worried. I just want to make sure I wasn't talking over anybody.
No.
I
No,
see your faces. I see you acknowledging everything. So we're good. Okay, cool.
Yeah. No, it was just really, yeah, I know. Yeah. And then I had the little glitch there of trying to figure out the sharing screen thing because I warned you ahead of time. It's amazing that I can do any of this because I'm so clueless about stuff, but we got that figured out now, so everybody can see that a little better. So yeah, this is absolutely, yeah, I can't wait to get into some more of this good stuff.
Yeah, I'm glad. So, any questions so far?
Here's one right here. Troy says, "Thank you for addressing the question about the Pleiades because he's the one who asked it in the first place."
Oh, yeah, I got to get back on topic. I still didn't finish that. Yeah.
Yeah, he says, but are they within each other's gravitational fields? I think.
So that's a great question because I don't know the answer to that, but I'm gonna give you my talking out of my behind answer, and then we're gonna find out together. I think we can get like an answer to that. But the reason I say in a way, and I'm sure this is subject to argumentation. I'm sure there's definitely like other arguments here, but I would say in a way, depending on their distance, because I'll give you an example. We talk about the solar system and, our our stellar neighborhood. And, we sometimes hear debates about, how much gravity should be in a given area or. That's interesting. Alrighty. Let me see here. I'm going to switch my screen real quick. Oops. Okay. I'm going to switch to shared screen. And, oh, wait. No, I don't have to switch the screen. I should have kept that one. Okay. So I got you. Give me 1 second. I know what I could have done. I'm going to take this window. Okay, so you might have to... Okay, good. There we go. Okay, so there we go.
Oh,
so the reason I'm putting this up is because... Okay, yeah, that's Earth right now in a space engine. And I adjusted the settings to make it, like, hopefully work correctly for what we're doing right now. I think it works correctly. Yeah, this looks fine. I forgot to activate my gamepad, so I'm going to be using my mouse, which might not be as cool, but it does look pretty. Yeah, it does look really cool.
It's still pretty cool.
Yeah, there we go. I'm going to turn on these green lines because these are really important for what we're going to do next. So what we're going to do is we're going to fly out from the North Pole. Okay, that's the lunar orbit. That's the moon. And the reason I'm showing this is because I have debates with coworkers sometimes, and this relates to the Pleiades. We're going to get back to answering the Pleiades question, so I definitely want to see that question again if there's any more detail there or any additional question, parts to that question. But the reason I'm bringing this up is sometimes my friend would debate me, and he watches some random Russian guy on YouTube, and he says that his intuition tells him the guy is right. That's subject to interpretation, I guess. But one of the arguments he'll pose, he'll say that dark matter was invented in order to explain why the moon's gravity isn't, or why the Earth's gravity isn't overpowered by the sun. Because his argument is that the sun is larger, it has more gravity, so the moon should be influenced, or the tides on the Earth should be influenced by the sun, not the moon. And the short answer to that is, look, I didn't research this myself, I'll admit. I didn't do the equations, I didn't do the mathematics, but the general idea is the inverse square law. And just like light the further away you get from something, it gets dimmer, or just like a space heater. As you move away from it, the amount of heat, gets, significantly drops off until it's almost nothing. And gravity is not exactly like that, but it's similar in that the Earth's gravity is going to have more, oh, I'm sorry, the moon's gravity is going to have more of an influence on our oceans, tides, than the sun because the moon is closer. So although the moon is smaller, it is much, 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 and that cannot be understated how much closer it is. When you're dealing with galactic distances, numbers get so big at some point, it's kind of just, like it just becomes like the numbers all sound the same, but it's much closer and it's pretty far away, but it's much closer. And so that's number one. But number two, the sun still does influence our tides. Apparently, there is a table or chart that does uh, predict or indicate times and dates of given solar tides. So I don't really know how much that affects the maritime industries, but of course, they have maritime schools where they focus on, like there's like I know a school in the Pacific Northwest, they literally would publish the tide tables that they would provide to the local merchant companies and to the Navy to use in whatever manner that the Navy would utilize that sort of thing. I mean, you want to know when there's high tide and low tide, when you want to park your boat near the coast, or if you want to make sure you don't bottom out when you're navigating a shallow, waterway. So my point in giving all that preface is that I'm using the sun as an example because it's kind of down to earth, pun intended. But it's near us, and we know logically, or I think we could assume logically. Okay, I guess we could assume logically that everything in our solar system, the 8 major planets and the dwarf planets beyond that, so Pluto and beyond, they're all subject to the sun's gravity. And one of the interesting things you'll see here is you'll notice that everything is on the plane of the ecliptic. And the plane of the ecliptic just means that flat, the bright green ring or the bright green group. So I'm on the side of the ecliptic right now. And when I go up, you got that circular disc. So everything up to Neptune, Uranus. That's right, I pronounce it as Uranus. I love on the science TV shows when they say Uranus. I feel like they're just trying to avoid the joke that people always make. Because when they say the name of that planet, people are like, oh, he said Uranus. But I think the Japanese say Uranus better, and so I'm going with the Japanese pronunciation of Uranus today. But yeah, so the planet Uranus comes right before Pluto and I'm sorry, Neptune. So you got Uranus, Neptune, and then Pluto. And you'll notice that all of the major planets up to Neptune are relatively on the same plane of the ecliptic or close to it. And you can see when we do the side view, they are in this almost flat plane. Like we can definitely see that here, right? And the only exception to that would be Ceres. And Ceres is on an angle, but that's because Ceres is not a major planet. It is a dwarf planet. It is an asteroid in the asteroid belt. We can take a closer look at that later if you guys want. In fact, just now I'm trying to click on Ceres, and I'm accidentally clicking on other asteroids. And this is actually not something I intended to show you, but you'll notice that while, everything up to Mars, the first 4 major planets are on the plane of the ecliptic, not only is Ceres on this weird angle here, but every time I accidentally click on another object that is in the same, area, we get these red lines. And you can see this red line here is on a totally wacky angle here. And that's because it's just an asteroid. This is an asteroid belt object, basically. And you can see that asteroid belt objects occupy the space between Mars and Jupiter. So you can see Mars is over here. There we go. That's Mars. And Jupiter is way out here. So the asteroid belt is somewhere in between. And Ceres is really cool. I'm glad they have it listed as a dwarf planet, because you can see, even though Ceres is a big asteroid, it's still an asteroid. It looks spherical. It looks a lot like our moon, as a matter of fact. We have pretty good... In fact, let's take a quick look at Ceres. I think that would be helpful. So just for reference, that's Ceres. Very moon-like. It's not quite perfectly spherical from what I can tell. I mean, just visually, it doesn't look perfectly spherical, but it definitely looks moon-like. So now, going back to just a wide diagram of the solar system, the point I'm trying to convey is that where's the North Pole? I always like knowing where the North Pole is. It just lets me get my bearings, It's not absolutely important I see the North Pole, but space doesn't matter what is upside down and what's not. But I like knowing where the North Pole is. I try to use that as my benchmark for orienting things until it becomes monotonous. Like there comes a point when you're flying around space in this app where it's like kind of pointless to do it. But this does relate to okay, I'm going too fast. This does relate to the same question. Don't worry, I didn't forget. I know this app is so cool. It's so easy to get distracted, right? All right, cool. So there we go. Okay, good. So now I know where we are. So okay, the North Pole is over here. We're gonna zoom out again. So bottom line is that my point is that the sun's gravity definitely has influence on the 8 major planets, and they all align to the plane of the ecliptic. Now that may be related to, you know, the early formation of the solar system, because at some point you probably had a disk of dust and material and rocks and gravel and stuff, and as larger objects come along, they sort of sweep it up like garbage collectors. And this is something that you can see in the rings of Saturn. As you know, when you see these empty gaps in the rings of Saturn, there's usually a moon in those empty gaps. But essentially, my point is that the major planets are massive enough and close enough that they pretty much stay on the plane of the ecliptic, and the only things that are not on the plane of the ecliptic are smaller objects like asteroids. But as you go further out, even if you have a planet that is moderately significant, like Pluto isn't humongous, but you know, it's decent. It's not huge by any measure, but it's decent. But as we get out there, we see all of the dwarf planets that we do presently have listed are all on these weird angles. And so I guess the point I'm trying to convey is that they're influenced by the gravity, but the influence of gravity starts to get weaker and weaker. And then we get to a point where, like, we got this dwarf planet right here. And this is like about Pluto size. So let's see here. Eris is 2,300 kilometers in diameter, 2,300 kilometers. Let's take Pluto for comparison. Pluto is about the same size, 2,300. Now, let's say, what's our moon's diameter? It's about 3,400 kilometers. So, you know, these are both smaller than the moon. But as far as the benchmark of Pluto goes, you see Pluto's orbit. Pluto is, actually, do you see Pluto's orbit? I'll show you Pluto. Pluto is that one. It's on a slight angle because you can see like this green line. And actually, it's a pretty steep angle, but it's so easy to mix Pluto's orbit up with the other one. But it's basically, you know, on a slight angle. You know, Pluto is, yeah, there it is. It's overlapping these other ones. But now we got Eris, similar in size to Pluto, and yet it is way off on that plane of the ecliptic. And just for reference, this is Eris. Now, this is not a real picture of it. I think we looked at pictures a week ago, but it's not much to see. You basically can get like the color of the light off of it, and then astronomers, real astrophysicists or real astronomers, they can use the light to kind of determine what kind of rock is that light bouncing off of. So, you know, we don't really have much beyond that right now, but we know it's there. We definitely know it's there. We, you know, have pictures where you see a thing that looks like a star, and it's moving like from like 1 month to another, or from 1 year to another. You see like an object that goes blink, blink, blink. So they know, you know, that we know that much about it. And so now we're going to go back north. And so Eris is like, you know, that's how Eris is influenced by the gravity. But wait, there's more. And then there's going to relate to something. We're getting there. But, you know, giving a little foundational stuff here. What's the name of it? Sedna. About 900 kilometers in diameter. But I just showed you Pluto was like, I think, a 280-year orbit. Eris is like a 600-year orbit, if I remember correctly. It tells us right over here somewhere, 560 years. Sedna is on a 12,000-year orbit, and in fact, it's treated like an asteroid, but it is effectively a dwarf planet. And because it's just like 50 kilometers smaller than the next dwarf planet, so I don't see why it doesn't count. But this is the orbit. This is a 12,000-year circle right here. This would take 12,000 years for this particular planet, and it just so happens to be near us right now. But essentially, from what I can figure, this is sort of like, this is my own intuition going on here. So, you know, speak to your local real astronomer if you have any doubt, or, you know, run the numbers. But I mean, you know, based on everything I've learned so far, I think it's, you know, reasonable enough. It's not as strongly influenced by Earth's gravity. So it was allowed to get into this really wacky orbit, or it was allowed to remain in this really wide orbit. But how does this tie into like the stars? Well, stars are nowhere nearly close to each other as, you know, our own solar system planets, including the objects of the Pleiades. And we can get a readout on the distance on that. But even in this context, the gravity does extend this far out. It's very significantly diminished. And sometimes people, what they'll do is they'll take like a trampoline and they'll put like a ball on it, like a lead weight, and they'll make a dip in the trampoline fabric. And that's sort of a good analogy. It's not entirely accurate, but it's a reasonable analogy for what's going on with gravity, because essentially if you have like a ball on a depression in the trampoline and it's spinning around, getting its centrifugal force going, that sort of behaves like orbit. It's certainly, I think it's a good way just to demonstrate it, like, to kids, or just to help like bring it down to earth to someone who's like not really into the whole, all that, what's the word, all of that abstract stuff, like, the fabric of space-time. It's like, okay, what does that actually mean? Well, don't even bother. We'll just use a trampoline. And I did bring up dark matter. I don't know anything about dark matter, but I'll tell you right now, it is heavily, it seems to be pretty well contested. And it's not just the pseudo-scientific circles who contest dark matter. There are, maybe they're not as widely notable, but there are real scientists, people who like don't really doubt the body of scientific knowledge that they generally that they generally come across, who do debate against the presence of dark matter, or at least they don't like the direction of dark matter research, because a lot of times you'll hear them talking about, we're going to build this billion-dollar machine like the Large Hadron Collider so that we could discover dark matter. It's like, okay, it's good to smash atoms together. You do make some relevant discoveries like about the nature of atomic stuff, but it's like, you can make an experiment, you make a hypothesis, you do the experiment, and it's like, well, all you can basically just make a claim. It doesn't really translate to something that people really understand, so it's not really a helpful tool sometimes. Like, maybe I'm missing something, but there's a lot of debate about how useful that technology or that particular particle accelerator is. Like, what benefit is it? Like, yes, if you build a really big particle accelerator the size of the solar system, we could probably make some really interesting elements and build some really interesting stuff. But other than that, it's like, it's, at the moment, this doesn't seem helpful. But I could be wrong about that. But the main thing is dark matter is, my coworker, way he described dark matter is wrong. But the general idea is not entirely off base, that there are things about, when you start looking at, like, okay, look at a solar system, gravity makes sense. The things are doing things that make sense, including what we just looked at here so far. But when you start looking at the galaxy, they question, like, well, why is it that everything is spinning at the higher speed on the outside, or why is everything spinning at a lower speed on the outside? I forget which one it is, but something about the speed at which things are moving on the outside of the solar system doesn't always check out. And so essentially, when you have your equations, if you're a real astrophysicist, I would treat dark matter as a placeholder. Like, you're putting it there because when you put this placeholder or this variable in there, it works. Like, the mathematics checks out. But even though the claim is that dark matter is not physical matter, it's not stellar dust, I think that still stands to be determined, because the way I see it, we are measuring that which we can see. There's a whole lot that we cannot see. And I don't see, like, personally, I don't see why we should simply discount dust or rocks or things of that nature. You know what I mean? Like it's like, if you have a lot of dust between here and there, that might make the difference in some of that math. But I don't like I was watching a video, someone explains why dark matter is real, and they did their best, and they're pretty good and on point, but I don't know. They seemed a little dismissive of those questioning it, and they didn't really give me like anything that I could comprehend. So that bothers me. But what this relates to the Pleiades is our nearest solar system, right? So, well, it's not solar system. It's a star system, I guess, right? Because our system is the solar system. But if we fly out, our nearest star system is Proxima Centauri. And so, just to give you a reference, we were here, right? That's us. And I'm flying out, and this is it. This is only 5 light years away. And I'm going to center our view on Proxima. And Proxima has a friend named Alpha Centauri. So we fly out from Proxima. Proxima is so dim you don't necessarily see it sometimes. You'll see Alpha Centauri, but not Proxima. But if I fly out from Proxima, I could do this routine here where I can see its neighbor. So let's see if we can find a neighbor here. I think that's Alpha Centauri right here. I believe that's it. Yeah, that's Alpha Centauri. So we're gonna go back to Proxima now because it's closer. But I just want to give you guys a reference here that these are only like I think a half light year apart. So you can see the star in the foreground here that I'm allowing to spin around. It's only half a light year difference. And I think I can see the Pleiades in the background. So that might, I think if that's the Pleiades, that would be awesome. If not, we'll go to the
That
Pleiades
would
next.
be.
But right, looks like it. So our gravity doesn't really affect Proxima Centauri, but technically the way gravity works, no matter how infinitesimally small, the influence of our gravity can extend it that far out. And one of the things I wish I did, but I'm glad I didn't enable the Oort cloud in this app. And the Oort
Mm.
cloud is sort of like this spherical area around our solar system of rocks and comets and ice and stuff like that. And it differs from other things. Like, so for example, the asteroid belt is like a belt of asteroids, but you just saw earlier how some of those things were not exactly on the plane of the ecliptic. They were on all kinds of different angles. And you have the Kuiper belt just around Pluto's orbit or outside of Pluto's orbit. And it's basically the same concept. It's a big ring. It's like the asteroid belt, but it's way out there. There's a ton of objects in there. There might even be things that are dwarf planet sized, maybe even one real sized planet in there that we have yet to see. But that's one of the arguments we get is like when you saw Sedna before, you saw that really weird orbit. Some people argue that there is a really large gravitational body on the outer edge of the solar system that we have yet to discover. But you know, of course, there's a lot of debate because it's like, well, come on, how would you not spot something the size of Jupiter? And you know, like we can go back and forth on that. I don't know where to begin, but it is an interesting question. A good friend of mine made a really good case to dismiss that possibility, and his words are not lost upon me. His logic is sound, but I'm still open to that possibility because it does solve a lot of the confusion about like why certain objects tend to have certain objects have an inclination in a certain direction when it comes to their orbits. It kind of like having an object, a random large planet out there would make it easier to figure out why. But essentially, gravity is one of those things, sort of like radio signals. It'll keep going indefinitely. Gravity will go indefinitely, but only, but it becomes irrelevant how far gravity can go once it's drowned out by other sources of gravity. So if I have a radio signal in an empty space, or if I have a sound source in an empty space, that sound will go pretty far away. But now, like if we're in a gymnasium, you hear me in the corner talking to myself. Let's just say I'm like a crazy man in a random gymnasium talking to himself. You can hear me from the other corner. But then you get like 10 people in there talking. You're gonna probably already lose the ability to hear me speak. Much less if you have 100 people in that room. And that's sort of what's happening in space. Like if you had absolutely nothing from here to like Proxima Centauri, and let's just say like another 20 light years out, you had nothing else, then yeah, the sun's gravity might have some influence. But obviously, just like the moon being, the way the moon interacts with the Earth and the moon have more impact on each other in the immediate term than the sun has on the moon. Than the sun has on the Earth. Like outside of the fact that we're orbiting the sun, the moon is going to have a more immediate impact on us. So if you have an asteroid coming into the Earth, if it's like that movie When Worlds Collide. Okay, now I'm thinking about sci-fi. That's irrelevant. Good movie though. Not a good movie, but a fun movie. Briefly, When Worlds Collide, I think like a large world-sized object is approaching the Earth. It creates some earthquakes and tectonic activity. It's a 1950s sci-fi movie, so take it with a grain of salt. The launch vehicle, the rocket in that movie is really cool. It's a rocket on a railroad track. It goes down a steep ramp, and then it goes like that. And like it's actually a smart design. It's a shame we don't see that technology used, but there's reasons why it may not. But anyway, bottom line is the point of that movie, I guess, is that large planet passes by the Earth. It's going to have a more immediate effect on us than, even a large object further away is the gist of it. So bottom line is that, like we may have a minor relationship with Alpha Centauri gravitationally, but certainly, Proxima Centauri is going to be more immediately influenced by its own parent star. But essentially, the weird thing is that when we talk about that Oort cloud, I guess the point I'm getting at is when we get to the Oort cloud, it goes out pretty far. We think of the Oort cloud as something that goes out okay, so let's see, where 1 AU is the distance between the Earth and the Sun. So if we try to approximate 1 AU, and we can just say, okay, that's 2 AU, 1.3, 1.0. So does that give it to me in kilometers? I don't think it does. Why am I getting a message right now? But anyway, right, maybe I guess the. Don't know. I just gotta tell you.
That's good. That's still like just really cool looking at the sun like that and all the
Yeah,
stars and stuff.
I,
Like
I
that's
chose
just cool.
I chose the diffraction spikes that look like a cross for, both for your show, but also because I think it
Mhm.
looks cool. Because like
Mhm.
depending on the type of camera you're using, or the type of telescope you're using, the type of aperture, or the type of the front of the telescope, like we talked about how the
Mhm.
mirrors are installed in
Right.
telescopes last time,
Yep.
and like the way the Hubble is designed, you get these cross-shaped spikes, but the James Webb Space Telescope, you get the other shape, and we do have James Webb in this app. At least we can look at James Webb. But first, the Oort cloud is okay. So that was 1 AU is however many million kilometers. I forget what the number is. I was hoping it would convert the number for me, but it doesn't. I think when you go to like point 0.5 AU, it gives it to you in millions. Okay, point 0.7 AU is about 900. Okay, 453,957. So it's like 10 million kilometers is point 0.7 AU. So we're just gonna round it up. 12 million kilometers per point one. So I don't know. It's like 120 million kilometers, give or take 100 million. But jokes aside, 1 AU is the distance between the Earth and the Sun. So now we're going to go way out, and now we're closer to like Neptune's orbit, and we're now already like 40 AU out. Okay, and now
Okay.
we're looking at it from like
So
about 200 AU. Now the Oort cloud is anywhere from 1,000 AU to 3,000 AU. So it literally covers the space from here to here, like approximately, give or take a few. But even when you go beyond that 3,000 AU, it still
mhm.
has influence out to zero point 0.1 light years, for example. And, in theory, you could have things from our Oort cloud still going out way further out. The only caveat is that if we turn on comets in our solar system, you'll notice an interesting pattern about the way that they move around. Where are comets? Okay, so we don't want procedural objects. We only want real objects. And there we go. Dwarf moons, asteroids. So we're gonna turn on comets, and
Wow.
this is not a comet per se. What you're looking at right now is just like their orbit. So we're gonna go back inside our
Uh-huh.
solar system, and I know it's a very
Wow.
busy screen. I'm
That's
lost now.
crazy.
So we are here. Wait, where are we?
We
We're
need one of
here
those little
somewhere.
you are here signs on on there so we know where the earth is.
Okay, so you are here,
Wow.
and because it's summertime, this is kind of cool actually. I like during the solar eclipse, I did record a
Mhm.
video, but I could demonstrate what I did on the solar eclipse. I simulated the solar eclipse in here because it was cloudy. So while I was trying to photograph the lunar eclipse, the clouds got really thick until it was like pointless to even
Mhm.
try. And then at that point, I was still like kind of curious. So I ran it in here, and you can set the date and time in this app and rewind and fast forward it and actually like monitor, and confirm that what you see up there matches up with what you see on the screen. So if you ever get into a debate like what caused the solar eclipse, well, maybe I can't confirm every detail, but I can at least confirm that what I see there is consistent with what I see here. Beyond that, we can argue all day. But you can see how like it's the light in the wintertime, this line would be way over here. And what's happening here, of course, now in the summertime, you're gonna have like, the midnight sun, so to speak, right? Like if we do
Right.
like just for fun, if we do like this, you can literally see like there's areas that
Uh-huh.
never get cast in night light or that get very little night light. So I think that's kind of cool and random. But anyway, so while we have everything on the plane of the ecliptic, these comets are all over the place. I mean, okay, you see this. I know it's hard to see, but the Earth is still here. We're gonna fly out on a slight angle. You can see the sun is the brightest object in the middle. Okay, so these guys are all influenced by Earth's
Wow.
gravity. But now, which comet do we want to pick in order to like kind of see what else they do? Now, essentially, the thing about a lot of comets are they're not all subject to our normal orbit. Some of them are,
Mhm.
like some of them. Okay, here we go. I found a comet that is on an orbit, like an actual orbit. Because like some of these are not. I mean, they're on an orbit, but they're also like on a trajectory where they're leaving. But I know this is just a random one here, but you can see how this has a loop here. So
Mm-hmm.
this guy here is, actually on a really elliptical orbit, but it's definitely an orbit. These other ones look like they're going out to nowhere, And then Halley's Comet, I think we can find. Let's find Halley Comet. Halley's Comet. How do we spell it? Halley. Wait. Okay, there
I
we go.
can't
So
spell, so
okay, so here's Halley's Comet right here. I don't know if that's a
whoa.
real picture or a simulated, a rendition made up by an artist. But
Right.
either way, it's a rocky thing that has ice on it somewhere. And depending on what stage of its orbit, and I believe this app can simulate cometary tails, but it doesn't do it. Why is it not doing it here? Is Halley's Comet is way out there. And in fact, let's turn off the comets now because that's a little busy to screen, but also because we now have a comet we can actually focus on. And you can see how there you go. See that red orbit right there? So you can see how it's just a lot. It's not in a circle at all. It's a really long ellipse. It's a really long oval.
Mm-hmm.
And just for the fun of it, we're gonna do something cool. We're gonna go back to 1986. I think we should do that. Just see what happens. And I know we got to get to the Pleiades. I know I got really
Yeah.
sidetracked here having fun with this here, but
That's okay because it's cool. So I'm okay with that.
now was it 1986 or was it a different year when it went near the sun?
I
Maybe it
think
was
we
a
looked
different
at
year.
the space cloud last time because we looked at those stalactite
Oh
mite looking
yeah.
things. Yeah.
So basically, what I was just curious was if I can get Halley's Comet to go near the sun. Okay, there we go. We're gonna go in for a fly in. We're doing warp speed or something like that, and I don't know. Is it going to show us the cometary tail? That's the whole reason I'm doing this right now. Okay, so Halley's Comet does not have a tail. Oh, wait, am I on the wrong side of the orbit? Oh, okay, we got to go closer. Okay, we'll go closer. Let's see here. And we're just advancing the calendar. I think it flew by around 1986. That's why I jumped to 1986 to try to get that close flyby. Because if I recall correctly, that's when people were able to see the ring of the tail of the comet. So I was kind of hoping that we'd see some kind of tail here. But I guess it doesn't want to cooperate today. Or maybe I disabled the tail. Oh, there we go. Cometary tails were off. Now it's on. Okay. That's in
Wow.
line with what we would expect. So now, this is not, this is a simulation here. I don't know how much of this is stylistic, but it's safe to assume it's all stylistic. But the general idea, the principle is there. You got heat from the sun making that ice out gas. You got other interactions going on. So sometimes you'll hear people talk about this thing called the electric universe. And the big problem I have with the electric universe is they tend to assume that everything that is known about space is mutually exclusive from their theory, and that their theory is accurate, and that everything else is the highway. And I don't buy that at all.
Mm-hmm.
I think that if anything, I see a gross misunderstanding of how all of this works when they when they insist upon that. But it they do at least point out, yes, there are electrical interactions. You have charged
Mm-hmm.
particles from the sun. When you hit water vapor or steam or whatever comes out of the outgassing with, charged particles, you're going to get some interesting things. When you send a probe there, you're going to detect a lot of things other than just ice and dirt. But essentially, it is ice and dirt, And so what happens is at different stages of its orbit, like you'll hear about comets in the news. I photographed a few comets and with varying levels of success. Like the Chinese comet. I see if I pull that picture up later. But if we fly out, I believe the cometary tail should go away because really it's only
Mm-hmm.
being influenced by the sun when it's near the sun. And once it's away from the sun, that tail looks like it's already shrinking. And yeah, that's accurate.
Mm.
So that's why when you often see a comet, you don't see the tail. And it depends on what stage of its orbit it's in that you would see the tail, And essentially in
Wow.
space, ice and water doesn't really stay unless it's cold and unless it's in a place where it can stay solid. The minute ice is exposed to sunlight, within a appropriate proximity, so the moon, Mars, even Mars's orbit, but once you get further beyond, like around Jupiter's orbit, that's when ice will remain solid ice, even when it's exposed to sunlight. But any closer or significantly closer, like when we get closer to Mars and Earth, all bets are off. That's why when they talk about finding water on the moon, you don't just find water anywhere on the moon. And even if you dig a hole in the ground, you find ice. The sunlight hits it, it immediately sublimates. It basically melts and turns into gas like immediately. But in parts of the moon, you have areas in the polar regions that are always cast by shadows. So that's an area where you might maybe make a ice water pipeline or something like that to run a lunar base, or maybe you build your base near the pole. But now getting to the Pleiades, because I know that was the original question. So short answer is not that I'm aware of, but we're gonna have a little fun here. We're gonna ask ChatGPT. Do the stars of the Pleiades does the gravity of the stars of the copy and paste the word I can't spell?
Well, here's the an update for the question, because he was wanting to know if the clusters of the stars in the Pleiades constellation are close enough to have significant impact on each other. So
Perfect.
do the
Okay.
stars in there.
So I basically asked a similar question, and originally, like I said, I gave you that long-winded answer, and essentially, what my short answer to that was, gravity can have a very far-reaching, for a large object like the sun, the gravity can go indefinitely, but realistically, any gravitational source is limited by other sources of gravity that drown it out. So sooner or later, there's going to be something larger or closer to something else that's going to essentially negate or make the gravity from a further away object irrelevant. So, of course, when we leave our own galaxy, yeah, the sun's gravity is absolutely insignificant compared to something that's like in Andromeda. But maybe if there's absolutely nothing between here and Andromeda, yeah, there'd be something maybe. But luckily, the Pleiades is another story. And I'm going to just give you the answer that this thing turned out. I asked a similar question. I phrased it a little differently. I asked, so it says, okay, so I said, does the gravity of the stars in the Pleiades influence each other? Which maybe it's a little bit grammatically off, but the ChatGPT understood. Yes, absolutely. Oh, and I should note, so in the paid version of ChatGPT, there's a button on the left that says explore more GPTs. And essentially you have like specialized ones. So if you like want PC hardware support, there's one that's trained exclusively on that type of stuff. Or when I was doing like video encoding, I had when I was trained on the documentation of the video encoding program that I was using. So it was more specialized, give me more, specific tricks. And in this case, I just typed in the word astro, which came up with a lot of astrology. So I added the letter N to ensure I don't get, astrology. And, there's a number of these astronomy and astrophysics related GPTs that are trained specifically on astronomy, text, and things of that nature. So presumably this will give a slightly, even though regular ChatGPT will probably do exactly what we're doing with it right now, when you start getting into the nitty gritty, if I was asking hey, I need help doing the mathematics for this really complicated thing, this would be the better way to do it to ensure that you're actually getting something that's, trained on material that is, relevant. So anyway, yes, absolutely. The answer, yes, absolutely. The gravity of the stars in the Pleiades does influence each other. Here's how that works. 1. Mutual gravitational influence. Each star in the Pleiades exerts a gravitational pull on the others because they are relatively close to one another. We'll find out how close in a minute. On the astronomical scale and bound as a cluster. Okay, that's true. They're a star cluster. They're a group, together. Their mutual gravity keeps them orbiting a common center of mass, much like a swarm of bees orbiting the hive. But, I would say, okay, that's interesting. I don't know if they have a common barycenter, but essentially a barycenter is a point between two objects. So when you have the moon and the Earth orbiting each other, the moon is basically orbiting around the physical Earth, but the barycenter, the center of those orbits, is actually a little bit off center. It's not in the middle of the Earth. And then if you take Pluto, Pluto has a moon that's about half the size of Pluto, or similarly sized, and the barycenter is way outside of Pluto. So even though its moon orbits Pluto, they really orbit each other more. Like they're dancing around each other, and their barycenter is literally between them. It's like there's a point in the Space Engine app where it shows you the two objects, and there's a little dot in the middle or a little diamond in the middle, and that's their barycenter. And so you could have different barycenters. If you take multiple objects and you count for their barycenters, I suppose you would have a common center, approximately. And certainly like if you take pictures of the same object, like with a really good telescope for 20 years, you can sometimes sort of see patterns emerge, and you can say, okay, this is the Barry Center. So, sure, if you know the mass, the size of the objects, how much gravity they can exert on one another, and their distances with relation to one another, you, in theory, a real astrophysicist can calculate or compute, use a computer to help them do it, right? Where that center is. But even with the mathematics, one of the reasons that we still use telescopes, we don't just assume that everything is a certain way, is because getting those visual observations and documenting them is critical in confirming things. Like, there's various experiments that are done where you can't really prove relativity in the conventional sense, although GPS satellites sort of take care of that. But like GPS satellites literally rely on relativity to work. Like GPS would not work if they didn't include relativity in the mathematics to make GPS work. But beyond that, it's all nebulous. And sometimes, like, there's predictions about, okay, if there's a black hole in the center of the galaxy, can we observe it? And we can't, but we have pictures taken over the course of 20 years where you see stars in the center of the galaxy. I'll pull that up in a little while. And they're orbiting something, and they're doing that slingshot maneuver and the elliptical orbit routine. And these stars, like, when you take into account the size of these stars, the distances they're going, you get an idea of the speed. But back to this here. Each star, okay, so we went over that. Much like a swarm of bees, which I don't know if that's a good analogy, but it's funny. The mutual gravitational influence is what gives the Pleiades its structure as an open star cluster. So yeah, short answer, yes. It allows the cluster to remain cohesive rather than scattering immediately into space. However, this cohesion is not eternal. What factors affect that? Okay, so just like all that nerdy stuff I was saying just now, gravitational interactions between stars can cause orbital changes, stars shifting position within the cluster. So this is why, sometimes like certain things break down, but this is why you periodically take new observations. Or this is one of the reasons why they have this new telescope. They named it something. I think they named it the Vera Wang telescope or something like that. But it was originally called the LSST, the Large Synoptic Survey Telescope. And the idea was it would take a really wide shot in each picture so that they could take a picture of the entire night sky every single night. And it would accumulate terabytes of data. But the idea was that if you take a picture of the entire sky every night, you could start to like maybe map out patterns, or if there's a supernova, you'd spot like a new bright object somewhere, and then other astronomers can then train their telescopes in that region of space, which often happens. Like when NASA was taking the space shuttle up, they had a thing called the Gamma Ray Observatory, and it's really just a telescope that they mounted to the cargo bay of the space shuttle. I think they mounted it to the robotic arm, or they stuck it in the cargo bay. And it was able to see gamma ray radiation. And so, every star emits all kinds of emissions, like radio waves, radiation of different types, ionizing and non-ionizing, and of course, visible light and heat, infrared radiation, ultraviolet, etc. And just like how we talked about last time, I can switch between different filters to take pictures in hydrogen alpha, which is a very specific wavelength of light, a very particular shade of ruby red. There's filters that eliminate, block most light except for UV. There's most of my filters block UV on purpose because usually UV creates more interference from local sources than as opposed to helping. But sometimes you want UV. But when it comes to radio astronomy, a gamma ray telescope is in this weird in between space because like it looks a bit like a camera, but it's seeing the type of light that we typically don't see. I mean, if you're seeing gamma rays, you're not in a good place. Let's just say that. You are not in a safe place.
Wait, you mean I can't be what was that? The Incredible Hulk? Who was the gamma race? That was the Incredible Hulk.
Yeah,
right?
yeah, you're right. Oh, yeah. Well, in that case, you're in a great place. you get strong. Hulk smash, right?
That's right.
But yeah, but the thing is, like, so what was cool was they used the Gamma Ray Observatory and they spot a bright emission of gamma rays and concentrated it in one spot. And then they were able to relay that information to Earth-based astronomers, like the coordinates, what part of the sky it was at what time. And then they point real telescopes at the object and they spot a supernova. They see, like, okay, now we know what created that emission of gamma rays. There's literally a star exploding or that just exploded. And the aftermath of a supernova, like when we think about supernovae, we think about let me see here. I just want to see if I can find it real quick. So like supernova discovered by Gamma Ray Observatory. So okay, SN 2023. Okay, that's a new one. Okay, well let's see what it looks like. So, oftentimes we'll have like one object spotted in another galaxy and it just comes up exceptionally bright. And then let me see if I can find a supernova remnant here. So, back in Chinese times, oh, that's cool. Is that it? Oh, that's an artist rendition. Who wants an artist rendition? I don't. No, I'm kidding. Kilonova. Oh, okay, I don't even know what that is. Okay. So anyway, okay, so supernova remnant. So when you spot a supernova, it might look like a bright star, but sometimes, like if it's close and big,
Wow.
like this is the Crab Nebula, and when this happened, it's documented by Chinese astronomers as being pretty darn bright. Like I forget if it's as bright as the moon or one third as bright as the moon, but it was bright. It was visible in the night sky. It was there for multiple months at a time. And fast forward to modern day, we don't have that bright object in the sky, but based on those records, when we point telescopes in that direction, we get this. And this is basically like what was left over. Whatever they saw was probably a supernova, and this is the result of that supernova. So sometimes we can like use records from like hundreds of years ago, and that'd be something that maybe in the future, if we do this again, Amber, maybe we can like try to like compile like biblical accounts or something. Maybe there's a few biblical accounts
Yeah.
that correlate to like real stuff that we can like actually like narrow it down and get like a little list together and just have them ready to go. Boom, boom, boom. I'm gonna. Well, I just that'd be cool. I know
You
that'd
know,
be right up
I've
your alley.
well, and yeah, and actually Troy here in the chat did a really cool presentation about the gospel story told in the constellation.
Oh,
So I'll send it to you and we
please
can go
do.
look at all that stuff. So we
Please,
will
yeah,
do
I'd love to
that.
see
That'll
that.
be
That's so
amazing.
cool. All right, yeah, that's good. So we got something there. So anyway, so let's take a look at the Pleiades now. Because bottom line is that the short answer is yes, but of course, different things happen to stars. Orbital changes, ejections. Some stars may eventually gain enough velocity to escape the area. So just like those elliptical orbits, kind of like the comets. Mass segregation. Heavier stars tend to migrate towards the center over time. Huh. I wonder why that is. I mean, it sounds
Okay, wait.
intuitive, but
I'm sorry. I'm just okay.
yeah.
This is breaking my brain. So I didn't realize that like stars move. Like you
Oh
just
my
kind of
goodness.
think of them as like this as the like center point of of solar systems, right? And planets orbiting, but I didn't really think about the idea that stars would move. Okay, that's kind of okay. That's blowing my
Well,
mind a little bit.
that's interesting because like the app I use doesn't always let me simulate it, but the second app might. But the gist of it is like we go to our Milky Way galaxy. So
Mm-hmm.
okay, we this is that's Haley. We're gonna go back to Earth, and we're gonna set the date and time to today. I'm gonna pause the time so my computer doesn't get overwhelmed in case I start pushing it to the limit. And we're gonna zoom out a lot. And before we zoom out, we should make a point of pointing out in the background there, that's the Milky Way. You
Uh-huh.
can see
Yeah.
we are in the Milky Way, but notice that um, if I spin us around, you can see how
Uh-huh.
like, it gets like, okay, so there's no Milky Way there, so that must be the edge. We're inside one of the spiral arms. And as we go here, we can see that we got this brighter area and brighter. Then it levels out again. It becomes dimmer, but you see some dust. And just like the picture I showed before, part of what we saw
Uh-huh.
was the absence of light from stars behind the dust cloud. So now that
Mhm.
we got that shown, now that I did that, we're gonna go back north. We're gonna turn on the orbits. We're gonna fly out like this because the sun orbits the middle of the Milky Way, but we got to go out way out. So we're gonna go with 300 light years out right now. In fact, I'm just gonna give you guys relative distances here. So 20 light years. Let's do this view real quick because this view is really handy sometimes. So this is cool because it shows you like everything,
Wow.
but it also makes it so that you can see things like, in fact, this is relevant because all these white dots are basically comets, or the blue dots are comets, the white dots are asteroids. So you can actually see the asteroid belt, but normally turning on the asteroids and the Oort cloud overwhelms the computer. Like to load the Oort cloud, I have to open up a separate plugin. So as rewarding as it can be, it's one of those things I should probably do as a video because then I can like
Mhm.
load the Ort cloud, and no matter how slow the computer is, I can still make a smooth video out of that because it can take its sweet time, processing it one frame
Mhm.
at a time. But anyway, so that's the relative area of the asteroid belt. Then we got a combination of asteroids, and once again the Kuiper belt is out here. You can see asteroids there, and you can see how they all don't conform to the plane of the ecliptic. They're all over the place vertically, but they basically have that like donut type of shape of to their orbit or the group orbit, so to speak. And then you got the blue ones, and the blue ones. If I click on a blue one, there you go. See, that's Comet 2011 McNaught. So a guy named McNaught must have discovered it, and that comet, it goes way out. So its orbit, does that mean the sun's gravity goes out to like a whole light year out? Who knows? I mean, or it does, but it doesn't. But essentially, what this is showing us is that this comet, either they don't really have the math in to determine if this is on a long elliptical orbit or if it's on a slingshot orbit. But some of the comets, especially Oort cloud objects, are things that were captured interstellar objects, things that were from somewhere else that maybe in some infinitesimal way were influenced by our gravity, but certainly as they got close enough to be captured, and they may have been influenced by the group of other objects that they were passing by in our Oort cloud as much as the sun itself. But you gotta this is gonna be a recurring theme when it comes to comets. You're gonna see this like very slingshotty look here. Um, but okay, so now this is 1 light year. So this is why I'm using this view is because we can see the light year representation. So 1 light year, and remind me to look at the Pleiades next. 3 light years, 4 light years. So there we go. 5 light years out, we can see Alpha Centauri and Proxima Centauri, and apparently there's a star named Alpro, not the dog food, Alpo. But yeah, we got a star named Alpro here. I didn't even realize it was there. And then we got like a Barnard star. That's like some of these have planets around them, some of them don't. But yeah, Barnard's has I think 1 or 2 planets around it. Then we got Ross 154. That's got some planets around it. I clicked on almost all of these, and some of them have planets, some of them don't. Epsilon Eridani comes up in science fiction a lot, so I'm going to just highlight that one because you can see here how, like, when I click on it, we get this triangle. So it's cool. It gives us this disk to give us an easy way to see the distance, but everything is still represented in 3D. So, when you're seeing the true distance, it's not just how far away from the center it is, but, vertically how far away. So this says 10 light years from the sun. But in this diagram here, it only shows it's about 6 light years. So it's accounting for that extra, hypotenuse, or you know what I mean? Like the fact that it's using a triangle to do that. So, okay, we got that. So now we're going to see where we relate to the rest of our galactic neighborhood. So we're going to go further out until we see oh, good, look at the Pleiades right there. So we can see the Pleiades in a minute, see? And the Pleiades, for reference, how far is the Pleiades? Let's click on it. So that says about 442 light years. So we're going to be going there in a minute. See, we already have it highlighted. California Nebula. And these are all objects in our own Milky Way, by the way. So when I showed you that dust cloud, you can zoom in on different parts of that dust cloud and see these really, like things just like that Orion Nebula we spoke about. And in fact, we got to revisit that because I configured the app to hopefully show us a more accurate Orion Nebula. At one point, I enabled a really fancy nebula, but it ended up making it look fake. So I disabled that because even though it looked cool, I want it to be, even if it looks ugly, I want a more realistic representation. So now, hey, what's up, James? Good to see you, bud. It's my pal James in the chat right there. So yeah, like that's the Milky Way there now. So just give you guys a reference. We're kind of like on this outer rim area here, and then we're gonna escape this now, and we're gonna zoom out from Earth a little bit more, a lot more, and look, the Pleiades is right there. That's the Pleiades at 400. In fact, let's rotate. Oh, look, oh, this gets weird too. So notice that disk of the ecliptic. So that's the galactic plane of the ecliptic, and the Pleiades is sort of like north of that, or if you call that north. We're gonna fly out more though because we really want to see like where we are placed in this, right? So first things first.
Yeah, I had
I
a
don't know what.
question about that. I don't know if we talked about it last time. I don't remember. But it seems like navigating in space would be extremely confusing because you're not
Oh,
just trying to figure out north. There's, like vertical and horizontal, and it that seems complicated.
you're definitely navigating in 3D, but the good news is that stellar navigation is pretty well figured out because for centuries we do this from the ground, where they use a navigational sextant to look at the angle of the stars at a given time of the day, and you can figure out your location as long as you have an accurate watch or a clock. And in fact, the Royal Navy was big on making clocks. They had to have an accurate clock on every ship at some point in 1800s, for example, in order to be able to like fix their location. And so when they started doing space travel, one of the things that they did was on the Apollo, the Apollo spacecraft, they actually did have a navigational sextant. I could probably find an example on my. Let me see here, Apollo navigational sextant, because they invented a computer that was amazing for the Apollo mission, and they kept it
Hmm.
as a backup, but they didn't rely on it. They just wanted to make sure they had a way of guiding the ship using gyroscopes. But really, the de facto way for getting a location fix was using your eyes. So while let me see if I get to pull this up here. Let me see navigational sextant, because we want to look at both types. So here's what one looks like, for a marine sextant. Actually, that's the term, not
Hmm.
navigational. But well, either way, I think it's the same thing. But that's a marine sextant right there, and you can see it's got
Hmm.
angles. You got little sunglasses built into it. You got a prism somewhere in there. You got a little telescope, and this is what you're using to kind of like point at the moon, the sun, or the stars to figure out where you are based on, like you got like a little bubble level in there. I'm guessing somewhere in there. I would hope, and the idea is that as long as you're holding it flat to the horizon, you can pretty much count on the readings you're getting out of this. The old, time tested, piece of kit.
Hmm.
And on the Apollo ship, they had this. And I know it may not look like much, but essentially, they would use this from inside of the spacecraft to get the angle of stars. And they'd have like either knobs or some method of controlling it.
Hmm.
And that's a lot of text. You know what's cool
That
about
is a
the
lot
you
of
know what's cool about the
text.
you know what's cool about the AI though? You could probably like I'm gonna ask the AI to do something really, really tough. You're gonna love this. You're gonna
Just
love this.
summarize it.
Yeah.
Yeah.
please please summarize this in less than one paragraph. So-
There you go. Because this has always confused me. Because like I enjoy watching like Star Trek and Firefly and some of
Mhm.
those things, and they're just like, all right, go to whatever planet, and then just click the thingies and off they
Yeah.
go. But then I'm like looking at your thing with the triangles, and I'm just like, wow, that looks complicated. Because how do you know like north? I mean, there even north in space if you're not on a planet? That's just
Well,
weird to me.
the good news about Star Trek, Firefly, and all of that is that like they're bending the rules,
Hmm.
right? Like they don't like have that fuel limitation. They're using essentially nuclear fusion to run their impulse engine, and so you get a lot more out of your propellant or whatever you're using to move around. You're not necessarily using propellant, but you're getting a lot more mileage basically, and that's really critical. But the thing is that to go anywhere beyond inside of a star system, going beyond just one planet to another, to go any further, you need to do something about that cosmic speed limit. If you can't go faster than
Right.
light, you're not getting anywhere in your lifetime. Like anywhere.
Right.
Like in like 5 light years, assuming you could go to speed of light, assuming you can go like just 1 point below the speed of light, you're still not getting anywhere faster. Like just like we talk about the Pleiades, 500 light years or 400 light years. So in sci-fi, once you're bending the laws of physics, once you're using a warp drive, things change a little bit. You know what I mean? Like you don't. But assuming that we're talking about intersystem, interplanetary, inside our own solar system, we never fly in straight lines. So I think one thing that's worth noting before we get back to that is, yeah, when you're in your own solar system, we like you saw the way the orbits are. When they send a probe out to another planet, they never send it in a straight line. Like if they could try to send it in a relatively straight line, but there's always gonna be like that curve to the movement. And that's because essentially everything's in motion. The sun is orbiting the center of the Milky Way. So like what I was showing before, yeah, that's what I meant to show you was, and I have the answer to that question. I said, how fast does the sun orbit the center of the Milky Way? The sun orbits the center of the Milky Way galaxy at a speed of approximately 200 kilometers per second. The orbital motion places the sun within the galaxy's disk, or the plane of the ecliptic, I would argue, or the galactic ecliptic, I would call it. I don't know if that's right now, but anyway. And its orbit is nearly circular. At this speed, it takes our sun about 225 million years to complete one full orbit, a period often referred to as a galactic year. This movement is governed by the gravitational pull of the galaxy's mass, including both visible and dark matter. Okay, see that word came up again. And the sun is currently located about 26,000 light years from the center. So basically, they bring up dark matter because the math doesn't exactly check out, and this is what they plugged into the equation to make it work. That's how I see it, at least. And once again, maybe it's a thing, maybe it's not. Maybe it's what we think it is. Maybe it's what we don't think it is. What they or we, whoever, the collective we, the collective they, the royal, you know how it goes. When someone questions science, they'll be like, they say this. They're like, who's they?
This makes me feel better about being bad at math, because if the math nerds can't figure it out, then that doesn't bother me as much for not being able to figure it out.
They're hardcore math nerds. Did you see the movie Hidden Figures?
Yeah. Yeah,
that was a good movie, and like those girls and that one girl. I remember the part where John Glenn was like, he wanted to get the landing coordinates, and they can only calculate within like a certain amount of miles, 50 miles or 100 miles, and he's like, on the radio, have the girl check it out, and like he wasn't comfortable going on that rocket until somebody guaranteed him that they would have the girl check it out, and the girl was that woman in the movie, and she really did check the math. Now they did give her a role in that movie at the end of the movie. She was not involved in the heat shield incident at all. But I get it. They wanted to put it in a scene with a lot of suspense. So that was cool. But what she did was super important, because at that point in time, they were just starting to use that IBM computer. And that machine could only calculate it to like a certain decimal point. And so, like, planning your landing spot off the coast of Florida, you still had a pretty broad search area. And so when you're trying to plan your landing, you want your aircraft carrier to be within a reasonable distance so that a helicopter can go pick up the guy, because that's how they would do it. The helicopter would go out, hook onto the capsule, lift it on the deck of the carrier, and yada yada, and that. But like, so they still need a human computer. As you know, back then the word computer was referring to mathematicians basically, and they needed a human computer to do this, and that's what that woman did. And it was super critical to like saving John Glenn a lot of time and ensuring he didn't get eaten by a shark. You never know. Sometimes like your capsule lands in the water, it takes some water, it starts sinking. You're sitting there on your raft, and then Jaws goes, oh, it's like it happens, So very important. But anyway, so like unfortunately, just, how I can fast forward space in here? I cannot fast forward the Milky Way. Like if I hit fast forward, you don't see any of this stuff move, unfortunately. But that's understandable. My computer would not be able to handle it anyway, I'm sure. But now let's go and visit our friend the Pleiades. In fact, we already have the Pleiades selected, so I don't know where Earth is, but one of the things I do in this app sometimes is I crank up the brightness of the stars like this. And the reason I do that is because it's a very helpful way of like seeing where our neighborhood is. And you can see like essentially this is all the stuff, or a lot of the stuff that we have mapped out. And I like, once again, these are artificially brightened. I cranked up the magnitude. Okay, so like this is like, this is the real magnitude 7, let's just say. But yeah, as your eyes adjust to the stars, you do see more things. The app limits what you can see to a magnitude 7 to simulate what you might see from the ground, like with the visible naked eye. But realistically in space, maybe it would look more like a magnitude 8 or you'd see more stars. You'd see progressively dimmer stars. So when I'm taking a picture of a galaxy or a nebula, I typically try not to do anything above a magnitude 10, because I know that that's going to progressively increase the exposure time. And remember, we're doing like we discussed last time. We take multiple pictures at the same setting, and we stack them. So if I got to take, 5 10-minute exposures versus 100 10-minute exposures, one of these, I might not even get it done before the season is over, and it's like, so at that point, that could be worked down the drain, because by next year, who knows, maybe I break my telescope and I got to buy a new one. So now I can't mix the pictures from last year, or whatever the case is. So I try to as I learned more and more, one of the things that I've had to do is kind of, figure that out. But anyway, so, and also it looks like Star Trek a bit. You got the colorful stars. That's one thing Star Trek also got right, was just having stars in different colors in the scene. If you were watching on a color TV, I know back in the day Star Trek was in black and white. But now we're going to go to the Pleiades. Oh, you know what? We're gonna do this. We're gonna go to Earth, then the Pleiades. Here's why. I want to see the Pleiades from Earth. I don't want to fly into the Pleiades from some other place. You know what I mean? Because then we might not be like this app because it's a 3D representation. Oh man, I forgot how to spell Pleiades. Oh, here we are. Because it's a 3D representation, you could look at any object from any angle. And, in this case, we don't want to do that. So there's the Pleiades right there. And we do have this button here that lets me pretend I'm using a telescope to sort of simulate what it would look like zoomed in from Earth. Wow. So we're going to start there and then we're going to fly into it. But I want to give you the flat, wide shot so we get at least a reasonably accurate representation of it before we fly into it. And then we're going to use this as an opportunity to kind of just see what type of distances, because like when that answer on ChatGPT said they were close, how close are they? Mm-hmm. And in the meantime, do you guys have any questions or any thoughts, either you, Shaun or Amber? Let me know if you got any thoughts or concerns or questions.
No, this is just so cool. Yeah, I'd actually love to hear Shaun a couple of thoughts because this is pretty cool.
Yeah, so this is in the meantime, I got the Pleiades here. If I rotate around it, we can certainly see it in 3D, but this is like the dirty windshield photograph that I talk about. And if I press F1, we can get maybe like just get an idea of like, well, what do we have here? Okay, so apparently this was the angle I think we were looking at it from when we were coming from Earth, if I'm understanding correctly. So if I type Earth in here, yes, actually that's what it did. It actually showed us from, did it do that? Maybe, I don't know. Anyway, I always get disoriented when I do this. All right, there we go. So we're going to go back to Earth. We're not going back to Earth, but we're just going to get the angle. So there's our Earth Pleiades angle right there, approximately. And now we're going to fly back in, and we're going to look at it in the picture form. But I just want to give you guys an idea because that's the angle. I'm going to bring it from top down just so I can see better. But we're dealing with, that's an 11 light year, 10 light year radius. So everything associated with the Pleiades is basically within this 10 light year radius. So yeah, they're pretty close, I would say. I mean, like our nearest star system is like 5 light years, and then the next one out is about 8 light years, let's say, and then 12 or 14, and this is a lot of stars in a relatively small area. So that's pretty interesting. And if we take maybe one of the sisters here, which there's way more than like 7 sisters here. Anyway, but the 7 sisters are the brightest ones. Okay, so maybe what we would do is say like, well, what's near this one here? This is Maya, apparently. Maya. So we're gonna take Maya. We're gonna zoom out from Maya.
Okay. So question. So those are held in that shape by gravity amongst each other, then, right?
I mean, presumably, I mean, that's kind of what we got from the answer there. And I don't want to say it's the, I mean, essentially, yeah. Like, I mean, like, and the interesting thing would be like, for how long? Well, I guess we could say this. We know as far back in time that the Pleiades has been documented. So we could safely say that they've been held together in that shape for that long, at least, because of their local gravity. So their own gravity, no doubt, has interaction with each other. So, for example, Maya, and Tauri, OU Tauri, is like 0.8 light years. It's less than 1 light year away. It's an orange dwarf star. It's about half the size of the sun. And then Maya is about 6 stellar masses. So, okay, that's a good example right there, because what that's telling us is that this one's bigger and heavier, like 5 times bigger and heavier than the sun. This one's half of it. So, yeah, I would say it's safe to say that in this type of distance, although this is significantly larger than the solar system we were looking at, because basically, like, I think we covered a whole solar system once we go out to, like, was it 1 light year, 0.1 light year? Well, the Oort cloud might go out, might have some extremities out to 1 light year. I got to double check that, but it wouldn't be surprising if you had some Oort cloud objects going out a whole light year. But in this case here, 1 light year for something 5 times the size of the sun, with relation to something that's half the size of the sun, that would be reasonable to say that these two guys, as a simple example, have a relationship, gravitationally, tied together. And it doesn't mean that something else isn't going to impact them, but let's go in closer to this one here. And this one is a blue giant, which means yeah, don't get close to it at all. Trust me, don't get close to it. You get some real sunburn from this one. Um,
Is
bring your
this
SPF 1 million, 10 million sunscreen with you.
is this one of those turn you into the Incredible Hulk kind of things here,
Oh, it
or
is.
like
It is. It's like this will split your atoms, make you crispy. Well, I don't want to over split your atoms, but it'll definitely like make you into jelly. It'll do that. Yeah, you'll become Odo from Star Trek Deep Space Nine for like a millisecond before. But no, I don't know. Yeah, it's basically like you said, Incredible Hulk. Yeah, that's actually a pretty good analogy. You're dealing with all kinds of stuff coming out of that. Um, so where is that other star? Well, I don't see it, but let's just click on a random star. 2 light years away. Okay, star Melati. Melati. And look at that, we got a little galaxy in the background there. That's Andromeda. Okay,
ooh,
that's way out there. But you know, you can see how like Andromeda, like at this distance, looks like it's as big as one of these stars, but of course it's way larger. And same thing, Andromeda looks like 3 times the size of the moon from our view, but of course it's way further out, and it's pretty huge to be able to be that big even this close. But once again, Melati is 6 stellar masses. It's 4 times the size of the sun, but it's 6 times more massive or heavier than the sun. So yeah, these guys all have like I'd say the proximity all within one. What do we say? 10 light years, and objects that are much that are like 10 times larger than the sun mixed into there. Some of them 5 times more massive in terms of density or amount of stuff, weight in there. Which I know weight is a relative term, but essentially the more stuff you have in one place, the more gravity it produces. Or if you take anything that weighs anything within a gravitational field and you're not orbiting it, you're not in free fall, you're standing on an object, for example, yeah, you're going to feel that weight. And although you don't typically stand on a star, if you orbit a star and you need to get out of the star's orbit, you need to expend more fuel or more energy to get out of that. So that's why it's relevant. But yeah, so that's the Pleiades there, and I do want to touch on the Orion Nebula before I forget. But before we leave not in particular the Orion's belt, but before we leave this neighborhood here, do you guys want to see any particular object of interest or anything at all that interests you?
So I do have a question.
Hmm.
So because you said this is all these stars are within 10 light years of each other, and then you said our closest star is like 5 light years, and there's another one with an 8 light years. Are we part of a star cluster?
Ooh, that's a good question. I would say no because star clusters typically like are visible groupings of stars. I mean, like we have stars that are near each other, but they're not quite as close. So, for example, like well, let me see if I got like a star cluster here. Was it M1 or M51? I'm gonna make up random M designations. I want to find one star cluster. M31. Hmm. Okay. Oh, golden eye cluster. Good. Okay. Golden eye cluster. Okay, let's see if the golden eye cluster works. At one point, I had an update on this program that didn't show star clusters. Some star clusters show up, some don't. This one apparently isn't showing up in entirety. Also, also I disabled fake stars. I don't like enabling fake stars because I just want to see the real ones. But there is a feature called procedural stars. It'll generate stars basically to fill in the gaps. But usually what I do is I load a data set called the Gaia data set. And in fact, that's what I need to open up because I want to show you that too. Gaia is a satellite that measures stellar distances, and there's an application they made that is similar to Space Engine, but it specifically draws data from the Gaia data sets. And so in Space Engine, what I do is I download a plugin or an add-on that
mhm.
takes the Gaia data set and it's repackaged to load in Space Engine. And they have basically like a version that contains 700,000 stars, 1 million stars, 5 million stars, 14 and 30 million stars. And when you load the 30 million star data set, the computer visibly slows down. Like it works, but the frame rate drops to below like 30 frames a second. So while I typically run this app at 60 frames a second to get that, well, I run it usually at 90 frames a second on my main monitor, but on a normal computer, like every monitor, every TV can run at 60 frames a second. So I typically set this to 60 frames a second when I'm doing a presentation like this. When I'm doing my own personal viewing, I'll usually set it to like either 120 or 98. And I kind of chose 98 because I found that 98 is like a reasonable compromise. Like it's a fraction of my main monitor's frame rate. My main monitor can do up to 200 hertz or 199 hertz. My upper right monitor does 240, but the way it works is that the higher the hertz, the less motion blur you get. And I found that like if I configure games to run at half of that 240 hertz, it's like it gives me like good motion clarity. Like it doesn't get motion blur when it's moving around, but also it doesn't overwhelm the CPU. And basically, after doing some reading, it turns out that's just the optimal setting, regardless for gaming and this and that. But the consequences is when I'm streaming, I know that sharing my screen at 120 frames a second doesn't make sense. Why would I overwhelm the computer? But even when I set it to this setting here to 60 frames a second, it visibly, slows down and gets all like, not choppy, but like just the frame rate. You can see like, like you can see it's going at like 15 frames a second. Like it's like I don't want to say choppy, but you know what I mean.
Mhm.
So Gaia is cool because I forget exactly how it does it, but it's in our solar system, and it orbits at a it orbits almost like we orbit the sun, and as a result, it gets pictures of from both sides of our solar system, and so it can use that data to calculate stellar distances, like using parallax measurements. Essentially, just like how we have two eyes that give us depth perception, so that we can determine, our brain helps us determine how far away something is. Is this thing coming closer to us? Is it moving away from us? Like, and it's all about that when each eye sees a slightly different image. That's why when you take two pictures with the right focal length and they're offset just the right way, you can take those pictures like a ViewMaster. You guys remember the ViewMaster?
Mhm.
Yeah, so just
Yeah.
like a ViewMaster, you take two pictures that are offset from one another, and our brain will interpret that as 3D because that's how that works. And with things at greater distances, you can't use the distance spacing of the human eyes. You need things to be spaced further apart. Like on a battleship, the thing that allows them to aim their main cannon, is spaced much more widely apart. They even have a thing that looks like binoculars, but it has like you look through it, like the narrow part of the binoculars, and it looks like a PVC pipe, and the lenses are like way out to the side, like out to here, let's say, and that's because that's that's what you need in order to like accurately measure things at greater distances. I believe they call that a range finder. And so anyway, using a similar principle, that's what Gaia does. It takes pictures on either side of the solar system at different parts of the year. It might use some other system I'm not aware of, but the gist of it is that its specific mission in life, its main purpose is calculating stellar distances, and it can also in turn calculate how fast things are moving. So it's helping us to refine the data because before Gaia and satellites like Gaia, you had an idea, but it's pretty. Sometimes you got a lot of like rough edges to these, to the mathematics involved in this stuff. So Gaia is really a big deal because like by being able to calculate stellar distances, I'm able to load a data set that accurately gives me the representation of different stars with relation to Earth and with relation to each other. And sometimes I can see more stars than what would normally be in the app. And so that might be why I couldn't. Sometimes I see star clusters, other times I don't see star clusters. So it's like loading the Gaia data set seems to help me load more star clusters. But we have this other app I just opened up if I could find it. Did I open it? I did open it up. I'm pretty sure. I
So,
opened it up.
which is this other one that we've been using though? Because
Oh, this one is called
somebody
Space
asked a
Engine.
while ago. Space
Oh, yeah,
Engine?
yeah, Space Engine. Yep. Here I
Okay.
got it on. I'll show you what it looks like on the window. So this is it's in the Steam App Store. You could probably buy it independently from Steam, from the website directly. But essentially, and I buy it on Steam. It is a free app. I paid for the paid edition because it had a few more features in there, like for content creation in particular. So not everyone would want to justify the cost, but I use the app enough. I like the app enough. I use it in my videos. So I said, you know what? I'll donate. I think it was $60, but like I see it as a donation for something I like a lot. I like what they're doing, so that's why I paid for it. But the free edition is basically just about as fully featured as the paid edition. So yeah, this is basically an app you can get for free, and that's what it's called, Space Engine, and it's got plugins, and in particular on Steam, they have the Steam Workshop, and so you can download ships from Star Trek and Star Wars. If you ever want to make like a video clip of a Star Trek ship, I know some people they like to make their own fan content when they make their own fan film. Sometimes you can like actually load a Star Wars ship in Space Engine and get it to look like it's orbiting a planet, although it doesn't necessarily do all of the pew pew, but it's still better
Mhm.
than nothing. But I use these plugins mainly to like either download realism overhaul, so like there's a mod that like makes things look more realistic, or sometimes maybe to make the color look a little nicer. Loading up planets that don't, that aren't listed. So in the case of our solar system, we load more accurate textures for Jupiter. So we get like Jupiter, we got pictures from 1979 from the Galileo probe. In fact, do I have the picture here? There's a cool plugin I saw today. I'm going to show you because like it's relevant to this here. So 1879, I think it was. Yeah. So this is a plugin that makes Jupiter look like it does from 1879, which might sound like
Mm.
really like why would you want that? But back in 1879, the red spot was larger, and you can see in this picture here, it's a little hard to see from this angle, but this is actually pretty accurate. It's very wide and elliptical, and the red spot is a bit narrower today than it was back then. So essentially, like based on the picture from 1879, it's shrinking. But I know you're looking at a simulated picture here. So how do we know it looked like
Mhm.
this in 1879? And this is apparently this is an old picture from 1879 of Saturn and Jupiter separately. These are not one picture. These are not one
Right.
picture. These are separate. But in both of these pictures, like okay, we see Saturn ball and a ring. It's like, well, that's sad. It's like that's the same Saturn that Galileo saw, and like probably for the first time or almost for maybe there's other pictures, but this is probably the first time or almost the first time that Saturn was imaged in that manner. And then you got Jupiter up here, and Jupiter's not much here, but luckily Jupiter is bright enough that even on the most antiquated camera technologies, you can get something. If you can get it in focus, you can get a picture of it, and they managed to do it. And so that's how, based on this image here, we know how big Jupiter is today. We have accurate data on how big Jupiter is. So if you take the size of Jupiter as you know it today and you assume that this object is the same size, you can then determine how big the Great Red Spot is in that picture. And that's how they were able to update. So that's one example of how you can use plugins in Space Engine. But typically, I use it either to load more objects. Like there's a JPL Jet Propulsion Laboratories has a catalog of comets and asteroids. So that's one of the plugins I'll load up independently sometimes. And once you get so many comets and so many asteroids that just like the Gaia data sets, it'll overwhelm the computer. And so you got to decide, like, depending on what I'm doing with the app on a given night or day, I'll decide whether I want to enable that or not enable that. And so that's sort of like, a la carte, I guess you could say. But Space Engine, my point is, like, I like it a lot. You guys have been hopefully enjoying what we're doing with it, but also,
Mhm.
it's a very handy tool, just for learning or even just doing your own rough, calculations. Saying, oh, like, well, like, like somebody's like, I had a coworker, and he's asking me like, why is the moon out during the daytime? And it's because he's so used to seeing the moon out at nighttime, he just assumed that it isn't supposed to be up in the daytime at all. And it's understandable. It's a common misconception. I mean, like throughout, anything, we see the moon at night. We see the picture of the night sky with the crescent moon on it. It's understandable that he would make that assumption. But the truth is that, oh, that's weird. Oh, man, it updated the Gaia app. And it's now making me re-update it. That's all right. I'm just gonna let the update run. We might not have it today, but I'll let it load anyway. And we're gonna load only the small data set so that we have if it loads in time, we can show it. But anyway, what was the question? Oh yeah, Gaia stars. Oh yeah, Orion Nebula. We should take.
Right.
What was it? I forgot I was gonna show you. I forgot. We'll go about the
Okay.
Gaia thing later, but if it doesn't even have to come up if we don't have time. But I'm gonna. Oh yeah, star clusters. That's why I was loading
Star
the Gaia app.
clusters.
I was hoping
Right.
that yeah, because like basically like I wish I could like I'm making up
Oh,
numbers here.
the question was, is the belt of Orion also gravitationally locked? That was
Yep,
the
that one.
question.
Okay, cool. We could do that one. That's easy. So let's
Mhm.
go to Orion. Yeah, let's go to Orion Nebula or Orion's belt, which is they're all in the same neighborhood. This is Orion's Nebula is between Orion's knees. And you know what? Just for good measure, I want to do this again. I want to go back to Earth real quick, just because I want to get the angle right. I want to approach it from where we are, because that's where we are accustomed to looking at it from. Okay, and Yeah,
Wow.
that's approximately what it looks like. I mean, like it's not perfectly exact, but it's about right. So now that we're in the right place looking at it, we're gonna go and fly into it. Oh, and
Wow.
okay, this is one of the reasons why I fly straight in too, so that I can fly backwards in a straight manner,
Uh-huh.
and we could adjust the brightness of the stars. And the reason I think that's important is because I want to make sure that we see right here. Do you recognize the constellation here? Oh, wait, actually, let me turn on the constellations.
Wait, oh, that's Orion. Yeah,
Yeah,
so
how do I turn on the? I want to turn on the constellation lines too, um, because like this is just showing us the regions of constellations, which is good, but we want the lines, right? There we go. Okay,
wow.
so okay, that works for me. So I don't know if we actually need the constellation boundaries. I don't think we need the boundaries. I'm going to turn those off.
No, that's cool.
But one thing you should note here is when you're flying in and out of the constellations, depending on how fast or far you're going, the lines start to bend. So you can see how like they're doing these weird contortions because obviously the constellations only retain their shape when we're at Earth. So we should go back to Earth one more time. We're gonna type in Orion Nebula again. We're gonna recenter it, and so that's the correct shape. See Orion the Hunter, as you're familiar with, right? You
Mhm.
see his arm is like,
Right.
he's holding a bow. I didn't know he was holding a bow. So anyway, but these are his legs, and although he doesn't exactly have knees, I like to say that Orion's Nebula is between the knees because um, it basically is. I mean, like it's in that. Yeah, those are the knees on a human being. Those would be the knees. So the reason I always say that is because you can usually see anyone watching the show right now can see, can see Orion's belt like in the night sky. This is one of the things you can definitely see. And I'm gonna zoom out a little bit more. And if I turn off the constellation, and I make everything else dimmer, it's like you can always see those even in a light pollution sky, or almost always you can see them. Or if you strain to see them on a bright sky, you can still eventually see them. So you're always seeing the belt, and once you know where the belt is, then you can usually spot the rest of it because usually the oh goodness gracious, what did I just do? Oops, I know what I did. I went in back. I crashed into our own planet. Oops.
Oops. I do that on a regular basis. So
There's another day at the office. So
that's right.
and I like to rotate, even though. And so about the navigational thing, Amber. So basically, the gist of it, what I was trying to say
Mhm.
before was, yeah, you use the angle of the stars. So ultimately, north south doesn't really matter. Although yes, it could be nice. Like if you live in a sci-fi universe, you might want your ship to face up along with the other ships. But chances are, spaceships will not be designed like a battleship. They're not going to have like a deck
Mhm.
plan that's horizontal. It's probably going to
Mhm.
be rockets, spaceships that are big are probably going to be designed like skyscrapers because
Mhm.
when you're under propulsion, when you're being pushed by your engine, you're going to be pulled to your seat. So if you have an engine that has more fuel efficiency, one of the things you might do is make it so that people are standing on the floor and the engine is below the floor. So when you're under propulsion, you have something like acceleration and gravity, so to speak. Like acceleration and gravity, as far as our brains are concerned, are the same thing. Even though, like, yeah, you'll feel the engine rumbling, the idea is that when you're in space, living or working in space, the longer you don't have gravity, the weaker you get. Muscular atrophy. You get something similar to osteoporosis. So, if we ever invent an engine that is more efficient but can give you enough propulsion to give you some, like acceleration, just like when you're being pulled to the back of your seat, except instead of the back of your seat being where you get pulled to, you're being pulled to the seat of your seat. So, the idea is
Hmm.
that sort of like if you were standing on the back of the seat in your car going, fast. Of course, in space, even half of g of acceleration will be better than no gravity. So anyway, um, point I'm getting at is that up is up, down is up. Doesn't really matter. What matters is that you have your bearings, and you get your bearings basically based on the angles of stars with relation to you. So from within our own solar system, we have it pretty well mapped out. As you fly further into space in the future, like if we're going like from Earth to the moon, we can use the slight change in angles to figure out where we are. That's literally how they do it now, or how they did it during the Apollo program when they were going to the moon. And when we send an unmanned probe to a really distant place, that's what they're doing too. They're doing the same thing. They're like they actually have a camera on them. They had like one of the spy planes we had back in the '60s had a camera on the top of it that would lock onto like a star, and then like if it saw that star, it was able to calculate the angle of that star and basically assist the pilot in navigating without GPS, without landmarks, because the plane would go too fast to use landmarks. This was an airplane that went 90,000 feet up. So to give you like an example, and so luckily that same technology that they were able to use on the spy plane, they were also able to use on the Apollo program to help navigate, the lunar vehicle and the whatever parts, the command module, etc. And so that's the bottom line: is you're using basically the same methods that time tested method that they've been using in, you know, whatever they call it, boating. So now we're gonna go fly
Right.
in, and so the question was about are they gravitationally balanced? We're gonna go to Orion's
Right.
belt, and we got 3 stars in Orion's belt, and I believe one of them is Mintaka. And anybody who watches Star Trek knows that the Battle of Mintaka was a decisive battle in the Dominion
Mhm.
War of season 7, 6, one of those seasons, the late seasons of Deep Space Nine. But jokes aside, I love when I spot science fiction stars in this. And let's see, that's Mintaka right there. So Mintaka is here. So apparently, in Star Trek, they went there, and obviously Mintaka, with relation to Earth, is far. Oh, that's cool. Are they gravitational? Oh, got a real treat for you here. We're gonna have a real treat for you in a
Wow.
second here. So we got something a little bit. The plot thickens here. So real quick, okay, we're talking about a light year distance of 1,200 light years between us and Earth. But looking at Mintaka, apparently this is one of those stars. Like, so there's stars out there. We call them double stars, where you point your telescope there, and depending on your magnification, it looks like one star. It looks like one star from the ground. But then, if you get enough magnification, or depending on what settings you're using on the camera, if you're using a camera, you'll be able to resolve a double star. So essentially, when 2 stars are next to each other, they essentially appear to be one bright star. But when you get that, magnification and everything is in focus and you get your exposure and everything is adjusted right, or depending on the type of telescope, you can sometimes do this visually with just an eyepiece. Sometimes you have to use a more. So in visual astronomy, you can change your magnification level by swapping the eyepieces out. So the eyepieces have different levels of magnification, basically. And so while with photography, I'm usually sticking with one focal length, whatever is being projected on the sensor, and that just works best for what I'm doing in that case. But when you're doing visual astronomy, switching out eyepieces can be really good, because it's like sometimes you have an object that's really bright, so you want to zoom in on it, and you're gonna when you zoom in on something, it gets a little bit darker. But then you might have another object that's like really dark, but it's also really big. So in that case, you might say, you know what, I'll sacrifice zoom so that I can get a little bit more brightness out of it, or whatever the case may be. These are things that you make a decision on the fly, perhaps, or while you're planning your imaging. So apparently, Mintaka is a triple star, if I'm reading this correctly. And I'm this is news to me as well. But we do know that when we look at Orion's belt, we see 3 stars. That's what we see. We see 1, 2, 3. And when we look over here right now, what we see here is, I'm going to fly into it slowly because I want to make sure you guys can see what. Because actually, when I click on Mintaka, it does list 3 stars. It has like 3 names at the top here: Mintaka,
Wow.
something Orionis, and 34 Orionis. I don't know what that symbol means, but anyway, so you get a lot of these weird symbols and names of objects. I don't know if they're Greek or what, but might as well. It's all Greek to me. But okay, so this looks like a double star, but I'm a little. Oh, oops. Okay, wait. So let's just hit the go. Okay, there we go. We hit the go button so I can center it. And apparently, yeah, we got like so these guys are definitely gravitationally linked to each other. Now the middle star of Mintaka, I guess that would be, is 24 stellar masses. I don't know what its diameter is. Oh, okay. So they don't measure the diameter. So normally in this app, everything is measured like with relation to familiar stuff. Like, or at least they got different numbers, but common numbers will be like 1 stellar mass. Or if you have a planet as like Jupiter, it'll tell you if it's like the size of Jupiter or if it's twice as big as Jupiter, because these are all relative sizes that we can grasp. Like, you give someone a number like 100 million kilometers in diameter, like that doesn't really mean anything sometimes, but if you say that this thing is 2.5 times the size of Jupiter, or 75% the size of Jupiter, then it's like, okay, this makes sense, So anyway, if we look over here, I don't even know. I guess it's the Barry Center? Huh. Anyway, I don't even know what that is, but let's click on this star here. Okay. So this is Mintaka here. Okay, this is a double star. This is not a triple star. I'm guessing that's the true Barry Center. So if I turn on Barry Centers, do I have them on right now? Um, hmm. I'm looking for the word Barry Center. Is it even over here? Ecliptic grid, constellation boundaries, Barry Centers. Okay, here we go. Aha. Got it. Okay, there we go. So this is the Barry Center, meaning that even though these two stars technically orbit each other, the reality is that, of course, you might say this star orbits the middle star because it's further out. And, for rough estimation, sure, yeah, it orbits that one orbits the middle one. But the truth is, and especially if we look, how big are they? 9 stellar masses, and this one is 54 stellar. Oh, that's combined. Oh, why does it tell me the combined mass? Wait, is that a double star? Oh my goodness. Okay, this gets wild. The plot thickens, Amber. So, okay, so that is a double star.
Oh,
So we really
whoa.
it's a triple group. So those two stars. Okay, so you got two. You got one star. This better be one star. Yeah, this is one star
Okay.
up here, and these are 2 stars. So those 2 stars, even when we get really close to it, close enough to see, resolve these two apart from one another, we
Uh-huh.
see that these 2 stars here, down here at the bottom, are still look like one star. So we're gonna fly in closer, and then we see the 2 stars resolve there. And these two, they have quite a ballet dance going on here, I guess you would call it. So
Mm-hmm.
once again, like, would you say that this guy here, this is Mintaka A, I guess it's called, and this is Mintaka AB, if I'm reading that. Okay, Mintaka AA, Mintaka AB. And I'm gonna guess they came up with these designations because they didn't know this was there for a while, and they probably already had names, and they were like, oh no, we already have Mintaka A. What do we call this? I wouldn't be surprised, but don't quote me on that. I'm sure we'll figure it out just by looking at this. But anyway, bottom line is that neither of them orbits the other. They sort of orbit a common Barry Center, and I don't even know where that Barry. I guess is that the Barry Center? Yeah, stellar Barry Center for Mintaka A and S Orionis A. So where's S Orionis A? Is this S Orionis A? No. Oh wait. Yeah, I think it is. Okay. So yeah, I believe it is. Okay, good. So bottom line is that, like, they're both so massive. What are their masses? Okay, individually. Why does it tell me the combined mass? I don't want to know. Wait, is that? I swear, if there's another double straw in here, I'm gonna go nuts. Okay. Whoa.
Whoa. Whoa. What in the world is that?
I'm trying to pretend to know what I'm talking about here, and I keep coming across things I don't know. Okay, but jokes aside,
Wow.
this is a double star and a double star, which maybe is why they had to come up with these weird designations. So individually, now I would say the smaller one orbits the larger one, but it looks like they have a bit of a weird relationship because this probably caused them to eject a lot of material. I'm sure if we looked at some real pictures of these, we'd see some pretty interesting things. So I'd say, yeah, Mintaka close-ups, whatever you want to Google, you'll probably find some interesting stuff. Maybe I'll give it a quick shot. That one there is 8 stellar masses. This one here is 24 stellar masses. So you got something 24 times heavier than the sun. You got something that's 8 times heavier than the sun. 6 times the sun's diameter versus 16 times the sun's diameter. And they're probably dancing around each other. In fact, but let's see. And I don't know if this is going to accurately simulate, but we're going to play them in fast forward and see what they do. Okay, so it's April 11th. We're advancing the calendar 1 hour a second. Okay,
Wow.
so that's interesting. So they seem to have a pretty fast orbit. And okay, so this is what I wanted to know, Amber. I wanted to know, do these things cross paths? Like, I was picturing this
Mm-hmm.
orbit, and I'm seeing that one side of this circle. I know it's really hard to see the circle, but I was thinking that one side of the circle would cause this little guy to graze the surface of the big guy. But it looks like they do orbit a common Barry center, and so I don't know where the Barry center is. I don't see it right now. I don't know if it's because the app is so bright. I'm gonna make those darker just so I can see what they're doing. I believe. Okay, this is actually very helpful. Okay, so we're gonna slow down time again, and what I would show is this red circle here represents the Barry Center, I believe. So I believe the Barry Center, yes, it's inside. So just like the Earth and the Moon, if you have two objects orbiting each other, technically this one is orbiting this one, but the reality is the center of its orbit is inside of this one. It's probably somewhere here, or here, I'd say, right here maybe. And so that's sort of what they're doing. It's kind of like this outer circle is kind of being moved in a circle along this circle, while this guy is also moving along this circle. I think, if I'm, or more accurately, this guy's moving along this red circle, and this guy's moving along this red circle because its movement is being influenced by its little brother, so to speak. And yeah, it's pretty interesting. So we learned something today, that this is a double star within a double star, and now that we know that, that's the thing, so we don't get confused. We know the mass of these are huge. So what we noticed was that we were dealing with some pretty like large numbers there, right? Like 16 times the diameter of the sun, 24 times the mass of the sun. And then we got the other guy right over here. And this one's a blue subgiant. So let's take a look at the blue subgiant over here. So this one is a single star. This single star is 10 times the diameter of the sun, 22 times the mass of the sun. So also quite massive.
That's big.
And so yeah, it's huge, right? And so like we got that, and then this thing in the middle is the stellar Barry center of both of these. So essentially, these two very massive objects definitely, like, even at these distances. What type of distance? Let's take a look at the numbers here. Oh, that's okay. Whatever. I like when the circle lines up, but it's understandable. Not everything is going to line up with the green circle, right? But that's okay. We can click on it. So let's take like the outer Mintaka here, for example, and we can see here. We're talking about 0.3, 0.4, like about a quarter light year, a little over a quarter of a light year. So absolutely, these guys like influence each other, but of course visually they look like one star from our perspective, so of course they would be close enough. And then let's go closer again, because I remember the Barry center is here. Okay, so that's like the common center, I guess, or is that the star? And where's the other star?
So how many stars does that make us up to now that are here? If that's
I think
three,
we got three, one,
we got
two,
a bunch of double
three.
stars there. Now I'm a little.
Yeah, well, so originally we had, I forgot. Okay, so you're right, Amber. So we had this double star, and then we had a double star in here, right? So
Yeah.
double star, single star. So that's three stars over there, and then when we get to the big Barry center, which is this diamond over here, we have another star up here, and this star here is also another double star. So wait, we have three down here. So let's go here now and see what we get. And we got two over here, and I'm not gonna pretend there's two here until I find out. Let's find out. This is a single star, so that's 5 stars in that particular area alone. And these are a little bit smaller. This one's only 2 times the diameter and 1.9 stellar masses. And this one here is 5 times the diameter and 9 stellar masses. So 9 times the size of the sun. So bottom line is, yeah, 5 stars in a place that I had originally assumed there would be maybe 1 star. But I mean, I wasn't surprised to see a double star. I don't know if these are things that, I don't know what instruments can resolve these stars. I don't know if any of the amateur telescopes can resolve these. That's something I have to look into, see if anybody's done that. Maybe it is a commonly done thing, but yep, that's one. So now let's see the rest of the Orion belt. And we're gonna go fly out. Oh goodness, I went too far. See, there's the constellations from far away, Amber.
Mm-hmm. That's wow. That's just. It just
bends.
well, and it too. It just amazes me, like because I'm not a math person, so
Yep.
I took as little math and got out of math as fast as possible.
I hear
So,
you on that.
but how it's everything is so it's this beautiful thing, but it's also very mathematically complex at the same time. So it makes this whole math equation come into this beautiful, like observable dance of complexity, and it blows my mind.
Hmm. Sometimes I wish they talked about this and rockets in math class more because I feel like if they gave me practical examples, it's like really rocket
Mhm.
science is give you an example. Rocket science, you're calculating how much fuel you need to carry a certain amount of weight or mass to like a certain place. But the more fuel you carry, you also have to then include in math how much more fuel you need to carry that amount of fuel. And part of the math is like as you're flying the rocket, you're losing fuel, so it gets lighter as it goes up. So you can find there's like a correct number somewhere in between all of those factors, and that's what the math solves. So the rocket science, although they do often say this is not rocket science, meaning that's not difficult, the reality is I'd say rocket science compared to rocket engineering is the easy one. Like once you get a
Mhm.
vague grasp of the math, and someone goes over and breaks it down for you, and if you're interested in flying a rocket or something like that, it becomes interesting enough that I think it would engage some minds of students. But sometimes I think they make the math so dry and boring in school, depending on who's teaching it, that like it doesn't even occur to you that it could do something cool like that, or it sounds so complicated, like it sounds unattainable. But some of this isn't. But this gets more complicated. But at the end of the day, a lot of it is angles, triangles. But anyway, so let's see what else we got. So now Orion's belt. Let's talk about Orion's middle star, which is also a triple star. Wow. Okay, so anyway, the group of stars that make up the single star that we see in the middle of Orion's belt buckle, um, that one there, how far away is it from Mintaka? Let's see if we can find out. So we're gonna go out however many light years until we see the next star. Okay, it's quite a few light years. Maybe I went too far. Oh yeah, there we go. Okay, so discount this star over here. It's way below the plane, I guess. But they all are. But anyway, Mintaka, or the group of stars that we call Mintaka, are about 29 light years on this disc here. It looks like about 29 light years both ways. Yeah, basically it's a little less than 29, but then it's 29 when you take into the angle there. So into account the angle, and you can actually see the flame nebula. So this, even though this view isn't focused on giving you the visuals of the nebulas, it does give you sometimes like for reference where a given nebula is spatially with relation to this stuff. So once again, that's where the mathematics is really important. Um, but short answer, it's a lot of light years. But as we discussed earlier, the gravity of something that's 20 times the mass of the sun. Give me 1 second.
That would be a
Hmm.
lot of gravity.
Yeah, so that's the thing. So I think like it overcomes the thing. Yeah. Hey Google, broadcast. I'll be down in a few minutes. Okay, I just had to talk to the Google intercom speaker real quick. I'm sorry. So anyway, yeah, I mean it's a lot of gravity, right? Or it's a lot of mass that would create a lot of gravity. So
Mhm.
its influence will extend a greater distance, and so it stands to be reasoned that these I would say Mintaka and Anila, and I can't read that name, Al Nilam, Al Nilam. A lot of interesting
I
names.
don't know.
Some are Arab names. Some of them are Hawaiian names. I think they started using Hawaiian names after they ran out of Greek names or something like that. So you'll see like a combination of like um, Arab names because those were some of the early astronomers, right? Then you got Greek names, and then you follow that up with Hawaiian names. Although I mean, it's not a hard and fast rule. I remember the movie. There's a book called Rendezvous with Rama, where a large cylindrical unmanned alien craft comes into our solar system, and they named it Rama because apparently in the book they said they ran out of Greek names, so they started using Indian names, like or from old
Mm.
Indian, literature, um, and it's East Asian Indian, not Native American, and um, like so in this case, I think they went with Hawaiian names instead. But anything where you can get a source of cool names, is sufficient. So anyway, Stella Barry Center Mitaka C. Oh no, we got another nested double star scenario here. So
More.
so
Wow.
yeah. So okay, let's start with the first one left here. So wait, are we back in Mitaka? Wait, we already do Mitaka? Wait, I'm confused. I'm confused myself. Oh, okay. Where's the rest of Ryan's belt? Okay, we're too far. Okay, we're doing this wrong. Okay, fly out, fly out, fly out. Okay, we'll go back to Earth. Then we'll go and do Orion. Then we'll center Orion. Then
Ah, there we go.
we'll fly in like this. Yeah, it's just easier for me to get my marbles when I do it like that, But if you were a man in a spaceship or a man or a woman in a spaceship, you would probably lean into your computer a lot. But I remember even in one of the better sci-fi books I read, it was a shorter story called "The Forever War" by Joe Haldeman, and
Mm.
like they had like a little porthole, a little window in the front of the ship. So if all else failed and they lost their navigational marbles and they needed to figure out where they were, this would be like your last resort. Would be like literally looking out the window with the navigational sextant and getting those angles. And sometimes like even on airplanes, they'll have like a bubble on the top of the airplane that they can use for that exact purpose. Like it's like a bubble you would use to like like a dome. Like you can look out the window and get your angles. And they had a vehicle in Antarctica. It was like a Russian diesel train, and it had a little bubble on top, so a guy could look out the window and kind of figure out in the spherical dome without getting exposed to the elements where they were. Oh gosh, I keep doing that. Okay, you know what's happening when I click on rotate? I forget
Oh,
that I'm rotating around something other than the thing I'm trying to rotate around. Okay, so that's Analam. Okay, so I just want to make sure because I mixed up Mintaka before, which is to the right.
mm.
So this is Mintaka, I believe, yeah, or the group of stars that make Mintaka. Now we're gonna go to Alanlam, and we're gonna zoom in on Alanam. Oh, I'm not saying it right, and we're gonna zoom out a little bit until we see. Oh, actually, that looks like a single star. Do we have a single? Okay, that's a single star. Amber, we got a single star.
Okay.
I think we got a single star.
No
Yay!
more, no hiding, no more hiding double play. Well, I'm sure there's more, but
Yeah. So now, if that's Mintaka and that's Analam, this is Al Nitak. Zeta Orionis, I think is another name. Oh, there's a double star. And that's okay. It's okay to be a double star, but it looks like
Mhm.
we got two double. Look at that. You know how we look at it? We can already see resolve the second one on the bottom. You can see how the diffraction spikes become a
Mhm.
double cross.
Right. Wow.
And we got this again. We got and once again you got like some beautiful nebula that we're much closer to that nebula. So one of the cool things to do in this app is like look at a sunset on another planet or something like that, and like sometimes you'll have a planet that's in a globular star cluster, and but I know it's a shame we didn't see a star cluster, but it'd be cool. I think is that the Horsehead Nebula? I think it's the Horsehead Nebula. Look, there's a little horse there. Yee! Okay, so anyway, um, we got these two and this one here. So bottom line is yeah, that's a single star right there. That is 14 stellar masses, 7 times the diameter. This one is 14 AU away from something. Anyway, that one is 20 diameters of 33 stellar masses. So once again, they're both quite massive, and with relation to each other, they orbit this diamond here. So they orbit each other, right? Like one doesn't orbit, like neither of them are the center of the other one. But when you take into account their mass and their proximity, how close they are to one another, this is what you get as the stellar Barry center. And you can see it's a little bit off the center between the two of them. And if we were to orchestrate this ballerina dance right here, we'd get something like this. Oh, Wait, I made a mistake. Okay, that makes sense now.
Whoa.
Yeah, so I forgot that this one's, so they're both like in their own circle, but essentially they both influence each other. So, but they both, and then
Mm.
in the grander scheme of things, yeah, everything's moving, but the question is like how fast? Well, not fast enough for us to perceive, but there are a couple of objects, like definitely objects outside our galaxy. If you're able to observe them throughout the year, you can sort of like calculate movement. But I believe there's one star with relation to Earth, and I forget the real name, but I think it's called Barnard's Runaway Star. So, Runaway Star. Nope, doesn't come up. So I want to Google it real fast, see if it comes up here. Barnard's Runaway Star, because oh, is it just Barnard's Star? Is that the same thing? Because we were already there. Okay, so this is a image of Barnard's Star and its surrounding. Copyright 2006. South is up. Okay, so I guess that's depending on where they were photographing it from. Barnard's Star is a little bit bigger than Jupiter. It's a red dwarf star. And this is a picture from. Oh, good. This is exactly. This illustrates the point I'm trying to make. So, this is just one example of one star, Amber. But when they zoomed in on it a lot, and they took multiple pictures over the course of like in 5 year. You got these are 5 year increments starting in 1985. Then they go 1985, 1990, 1995, 2000, 2005. And while these other stars might move a little bit, and you got to remember, like, these are being taken on different telescopes, so a lot of that movement is just the type of telescope or in different atmospheric conditions while taking the picture and other factors. But mostly these stars are more or less appearing to be stationary or moving minimally. Now, maybe some of them wobble a little bit, but once again, I couldn't rule out atmospheric disturbances being the primary factor. And also, it looks like in these pictures, they're really, in fact, I don't know if this is a sky survey that intended to focus on only these stars or if it was a broader image. But bottom line is that this white dot, it's moving. And like in these 5 year increments, we can see it's moving significantly compared to the background. And part of that is it is relatively close to us. But essentially, it doesn't move that fast. How far does it move? Well, over the course of like 100 years, I think 300 years, it would move like a centimeter or something like that. Like, if you look it up, you'll see it. But the gist of it is, last time I looked into it, it was like over the course of 300 years, it moved like every 100 years, it moved a number of millimeters, and I think it came out to being like this much. Like, so like if you looked up at the sky and you held your fingers up like that, it'd be like that much it would move across the sky. And that isn't really a lot, but over 300 years, when a lot of the other stars might not move as much as that 1 centimeter is huge. And in the picture you just saw, that was only a 20-year time span. And that's what great magnification, So when you if you zoom out from that object, that's how much it moves in that short span of time. It's not the most visible thing. So, and what I'm trying to say is that if that object was moving a whole centimeter in like 20 years, that picture, it would be moving a lot, more. But it moves pretty, I mean, it moves. The point is that, yeah, like you look at old pictures, it's always like, moving more than the stuff in the background. So that's one example of a star that does that. But the odd thing is that it's also Barnard's star isn't like terribly far from us. It's like, this is something that I really didn't do my homework on, but it's an interesting question. And so let's just see where we are with relation to this. So Barnard's star. So here's Barnard's star right here. And that's like 6 light years basically, or based on the angles and everything, or it says 5.87 light years. I don't know how much, I don't know if they're taking the triangle into account, but whatever. So yeah, that's how far that is. And apparently this guy moves a lot. It's got some planets around it. We got and I think these are based on real data. Of course, the surfaces are totally made up. I mean, we might have a
Mhm.
vague idea of what they're doing. I don't know if we even know what way they orbit. To be honest, some of the information is pretty spot on, and other times, like there's a lot of inferences going on. So, you got to take it on a case by case basis, but never assume that everything is as you see. But generally, if they say there's a lot of water on a planet, there's probably a lot of water or water vapor on that planet. And generally we have an easier time of spotting larger planets, so it's only a relatively new phenomenon that we're able to spot planets that are much closer to Earth's size. At one point we could spot planets that resembled Earth in terms of like compositions, but they were like 3 times the size. And we don't know anything about what life would look like there, if there would be life there. But once again, alien life by definition is alien, so I don't think it's reasonable to assume it's all going to be a certain way. But yeah, so that one moves. Unfortunately, I don't think this app will simulate its movement. But what I want to do is I want to grab the Gaia Sky app real quick, and I think it's on my top monitor. I hope it lets me move it. It does not. Okay, that's all right. I'm going to share the upper screen as soon as I find the window. Okay, there it is. And I'm going to switch my screen. Or I can just share the upper screen. Let me see here. Share screen, share screen, share screen 1. Allow. Okay, there we go. So now
Wow.
we wanted to, what was it we wanted to look at? There was something we wanted to look at that was relating to distances that Gaia can see. Well, let's take a look at Orion. Oh, star cluster, any star cluster. Well,
Mhm.
let's see if we can visually spot one, because I forget how to navigate. This is a different app, but essentially what Gaia is doing is this is what a Gaia satellite resides. By the way, this is its orbit here, and I don't know how to get to that. Right click on it. Oh goodness gracious! No. Okay. Go to object. Oh no! Oops! I went to like the other side of the known universe.
Oh man.
Alrighty. Well, anyway, I think that basically covers a lot of ground. I think at this
I don't
point,
know. Yeah.
give you
I
an
think
opportunity. If you have any questions, we're fine. I was trying to keep it short. I know it's really late, and I'm really grateful for that. I was able to speak at length. I'm sorry I didn't give you guys, I'm a little flustered sometimes, like, looking under the floor of the turtle tank to find my beloved Squirtle and all. But,
right.
I do appreciate you did give me a list of things. You helped me out. I made a list too. Maybe if I have an opportunity in the future, I'll try to organize a little better. I was surprised today was the 10th as of yesterday, but I was like, oh, it's the 10th. But I got my nap in, everything worked out. I'm glad
Right.
I had a blast talking to you guys. But yeah, any questions at all, either of you?
You had mentioned that you can plug in procedural stars, which don't actually
Hmm.
exist. Is that kind of the same thing as like paper towns for like map making, where it's not something that actually exists, but it's something that helps the map maker to determine distance?
Oh, that's interesting. I don't know, but I mean, it's certainly there for the aesthetics because some people use Space Engine more as a game than a tool, and sometimes they just want to go flying around and they want to see where they can find a planet with life on it. But of course, it's like, what baseline do we even have to determine that? It's like we only know one planet so far with certainty with life on it. So it's like not really, unfortunately, yeah, it's a stretch, but it can be helpful. You're right. Like, I mean, that's actually a good point because, like, a good example because, I could see where that could be useful in a place where you have a star where you think there's other planets in that star system, but you literally don't know. We just have not confirmed it at all. You have these suspected exoplanet scenarios, and procedural stars could potentially help in that regard. So, for example, one of the settings is procedural moons. So, while we have a number of, you know, exoplanets, stars that have their own planets outside of the solar system that we've been cataloging in relatively recent time, like the past like 20 years, basically, we, don't have any moons at all. Like we just don't really have moons documented. There might be like one or two suspected ones for all I know. Maybe they even have one, but there's no confirmed moons. And as we oftentimes with exoplanets, for the longest time, you weren't even directly imaging them. Even now, we don't always directly image them. Sometimes you're just looking at the star and they're saying, "Hey, the star's wobbling a little bit," and then they figure out based on the size of that star to wobble this much, the object influencing it has to be this size on this orbital period. And then and sometimes based on that, we were able to real astronomers were able to go back and look in a region to try to directly image something. And part of that trick would be like the telescope would have a thing that blocks the sunlight, and then like a I forget they call it a corona mask, I think they call it, and it blocks the sunlight so that it's not over exposing the rest of the light. And then that's how we could directly image stars. And so and by we I mean they. No, I'm kidding. But no, seriously though, like like so like direct imaging stars, and then the other method they used was now how do they identify elements in the stars as they're crossing paths with the planet, the sun? If the atmosphere hits at such an angle that the light from the star goes through the atmosphere, and they already know about the stars, spectra using the Pink Floyd thing, the prism with the colors and the absorption spectrum. They know basically what elements would produce that type of light. Then you can figure out what what types of spectrum get absorbed, or what parts of the spectrum are absorbed by the planetary atmosphere, and then basically they use that difference to figure out roughly what's in the atmosphere. And then recently I learned about this like a week ago. Apparently there's now a method where I don't know how long they've been using this method, but now if a planet doesn't cross in such a way that you can get its atmosphere to line up with its own parent star, there's a method of using bright stars in the background. So there's a number of really bright stars that are just exceptionally bright. You see these examples of stars that are multiple times the stellar mass of the sun, and they get pretty big and pretty bright. And so if they have a known, baseline on those stars, then if the planet's atmosphere, like if the star's light skims the atmosphere of that, like so you got the planet and you got this, light going through the atmosphere is this thick, and the light is kind of just going through that area, they can also now use that information. So that's how they get that figured out. But the idea of using it's pretty cool about the mapping there. You could definitely So I haven't really taken advantage of it much, but I
Mhm.
that means I don't really know what they do to make a procedural star. I'm pretty sure it's all like just like mathematics and automatic. And in a game like No Man's Sky, it makes sense that you wanted to generate a plethora of planets with different environments, different types of colors, and different trees and different animals. In reality, that game it's like mix and match. Like there's really only like 6 types of planets, but like on every planet you'll either have a horse that has its head on the head or a head on its shoulder. But at the end of the day, it's like there's only so many. It's like Mr. Potato Head. That game does it like Mr. Potato Head style. So that's my concern. Like I would love like, procedural objects followed maybe some kind of rule, like where maybe they prioritized um, what little we do know, maybe to help fill in gaps of what we do know. I don't think that's how it works right now,
Mhm.
but it can be helpful. Just to, like maybe, for example, if you have a procedural moon that is about the size of our moon, it can give you an idea of what would a moonrise or a sunset look like on that planet. And I would assume, but I don't know if they do this, that they don't put these things on in orbits where they can't belong. I'm assuming that when they put a procedural moon around a real planet, it's in something that is like a sustainable orbit. You know what I mean? It's not going to be in an orbit where it's going to like a moon the size of our moon is going to crash into the planet's surface a week from now. That would be an example of like unrealistic. But like I haven't really done any research. I usually avoid procedural objects because I just want to see the real deal. But it's interesting you mentioned. What's that term about the maps again? You told me.
Paper towns.
Paper towns. Okay, cool. No, I'm gonna look at that because that's actually a pretty cool. That sounds like a pretty cool thing to relate there. Cool. All right. There we go. Duly noted.
Yeah, so I just wanted to kind of to bring this around because these are questions that came up because somebody, I'm going to put this up here, sent me this out of Job 38. So Job 38, 31, 32, and 33. It talks about, can you bind the chains of the Pleiades or loose the cords of Orion? Can you lead forth the Mazzaroth, which they think is a constellation? Or can you guide the bear, which is another reference to a constellation? Do you know the ordinance of the heavens, and can you establish their rule on earth? And really interestingly, and when I looked at that too, that gets quoted in the book of Amos 8 and 9. So you've got this being referenced in the Old Testament. They're talking about these are constellations that we see God is referenced. And so now that's really cool to get to go and be able to look at these and see like all of and how intricate and complicated and amazing all of this is. And I love this because this gives you like visual pictures. Now you can kind of see, because we've looked at all of them. Um, you got this mental picture, and now with what is it, Orion, we had all those like double stars in there. It's just like, the complexity upon complexity. Like, how do you loose the cords of all those double planets? Do you like it? Just it's amazing to me, like what is happening with all
I think it's
this.
interesting that like when that was written, that there was even a
Hmm.
mention of these things having some kind of
Hmm.
relation there, and it's like, whether the chords are an analogy or someone's imagination, it's like it does kind of line up with what we are talking about in terms of
Hmm.
gravity and how these things influence one another. That's pretty cool.
Well, and there's modern scholars now think that actually Job was the first book written, that it's old enough that it was written before the entire rest of the Bible. So this is way back,
Mm-hmm.
um, in very ancient. This is still very nomadic. This is before Israel even existed. Like this is old ancient stuff here. So
Mm-hmm.
that makes it even cooler.
And that's the part of the world where they
Like,
took astronomy very seriously.
mm-hmm, mm-hmm.
Mm-hmm.
But it's just
Wow.
it's just cool to get to be able to go and see these links and then get to go look at this phenomenon up close in a way that they would have never imagined. I mean, but that we actually now with technology get to look at some of this stuff. So Shaun, I really want to know what you think at this point.
Well, so going from looking at Job, and then like you said in Amos, and then being able to draw the line from you know uh, Copernicus, Galileo, all the way to where we're at, and it's like all throughout history, at least our history. Um, we have been looking at the star or at the sky, at the heavens, and feeling inspired and in
Mhm,
awe of the creation of God. And now, obviously, because of Ronnie's help here, we've had the opportunity to almost go and
mhm,
visit those places, and it it doesn't. Sometimes when you look deep into something, it loses its mystery. I
mhm,
don't feel that way at all about this. I feel even more
mhm,
intrigued. I feel like there's more awe and more mystery, um, and so in a sense, we get to participate in this tradition of Christians looking at the heavens and just feeling that weight of glory. And so, because we've been able to do this today, we're participating in that Christian tradition of looking
right.
into the heavens and feeling that weight of glory. And so, it's just really awesome to be able to kind of add our name to the list of believers who have looked at the stars and felt
Mhm.
inspired.
What one of the
Mm-hmm.
things that I love when you start looking into the ancient Near East in the way that nomadic and semi-nomadic uh, storytelling culture and world that they grew up in. These are not just places that they're naming. These are like bookmarks in their story. So as they're traveling during the seasons and they're telling their stories, and then it's like, oh, I see that. I see Orion. That reminds me of this story and these characters. And I see, so they're markers and visual reminders and not just these phenomenon that would, I think, maybe confuse them, because these are like markers of their history, markers of their story, markers of their identity. And that to me is so beautiful, that something so complicated and so complex that we get to look at even more closely, in the memory that's held in those shapes and in those phenomenon. Like it just blows my mind.
Well, there was one person who had made the comment, and I had to chuckle because it's so true. About every time they find a new discovery, they go
Hmm.
and try to rewrite everything that
Yeah.
they've understood, and there's a lot of truth in that. It's this idea that, and this is hitting on what you had just said, Amber, that in modern secular society, we want to have truth divorced from meaning, but
Hmm.
you can't have that. And what the ancients had was they had a truth and meaning were coupled together, and so when they're looking at the heavens, not only are they looking at something, but they're looking at a piece of their story.
Mhm.
And unfortunately, now, like I said, the reason that people are so quick to throw out the narrative, to throw out the story anytime they come
Mhm.
across a new piece of information, is because truth and meaning are no longer coupled together. Um, and and that's sad. I mean,
Mhm.
I don't think you can have truth without meaning.
Yeah, I think that goes back to something that the Western mind has lost is this idea of collective memory, that we don't engage with that anymore because we don't have that anymore. And that is what, like, the Old Testament is full of generations of collective memory, and that is carried through. And where some of these ancient cultures that are still around have that connective, collective memory that is carried through. So when we were, I was visiting a Greek Orthodox church yesterday. Was
Oh,
that
that's cool.
yesterday? Yeah, that was yesterday. Good grief. And I was sitting there and looking at, they have all these, beautiful iconography all over the place. And I was just like appreciating the collective memory that's passed along from, that started collecting at creation, and they carry that collective memory there. And it's such a beautiful thing. And with really looking back, the Enlightenment that really unhitched us from that connection to the collective memory. And it's something that, you know, like Shaun, like you were pointing out, when a new piece of data comes through, we don't have the collective memory to be able to process new things. We just have to throw out everything because we don't have the weight of tradition to help us maintain our balance when new things come up. So it is really, that's one of the things I love so much about Old Testament studies is you get to tap into all that ancient wisdom and really try to bring that out in the mindset that was being written when you're looking at things like Job 31 and Amos 5, because these aren't just cool dots in the sky. These are collective wisdom and memory and tradition and things that we have lost in our instant modern world. And it really is, to me, a privilege and an honor to get to study. And so I love it so much.
Yeah, I gotta say, like, I've never really leaned into like the biblical relationships between what is known today or what we're presently learning, or personally what I'm learning a lot of times I'm learning a lot for the first time here, but like I'm fascinated by this. I can't wait to see that video or that presentation and see
Mhm.
what I can correlate. Because I mean, even like between like the Chinese records from like 500 years ago, we got
Mhm.
some stuff in there that's like that is a little bit easier to confirm 500 years back, 300 years back. That's a little easier to validate. But like even then, they didn't have the name
Mhm.
correct or any of that stuff. They just had like region of sky with relation to such and such and such and such. And luckily, we know okay. The moon has got it. If the calendar, and that's another thing, calendar systems, you go back in time enough, like I get myself confused. Like I tried lining
Mhm.
up the stars on the birthday of Jesus, and I'm not
Mhm.
even sure if it's correct. Like, I'm guessing the
Mhm.
leap years are being taken into account. I don't think they had leap years back, and so on and so forth. So like these are some of the things that like I don't know if this app is equipped. And also, as you saw, the app didn't really make
Mhm.
the Milky Way spin. And granted, over 2,000 years, it wouldn't really move a lot. Um, and so some people think that like when on Christmas Eve or whatever day Jesus was born. I'm not sure what the exact calendar date was in relation to what we know or what we rely on, but some believe that it wasn't necessarily a star or a comet. It could have been a planetary conjunction. So like in recent time we hear about when Jupiter and Saturn are like on top of each other or really lined up, and sometimes like just like we just saw with double and triple stars, how they sometimes are close enough they make one bright star. So if you have like three planets or two planets coincidentally lining up, or whatever the case may be, they're lined up. That may cause the planets that are already really bright compared to stars, in our own solar system. Perhaps if you have two or three of those stacking each other, especially Saturn and Jupiter, or Mars and Jupiter, or
Mhm.
any number, any two of them even, it comes out brighter. Maybe that was it. Maybe that's what people were seeing. I don't know. And
Maybe.
even then, it's just still a day of significance because to have a planetary conjunction, on that night, it's still kind of a, There might be more to that. That's all I'm saying. Like, I'm not expert. That's your
Mhm.
field there.
Well, your mic got a little quieter there for a second. But one of the ones I love to point out and talk to and show people kind of how this works in this collective memory. Like you see the wise men show up after Jesus is born. And you're like, they show up to Herod and they're here and this is how we got here. And you're like, well, how did they know that? And the one of the working theories that I think has a lot of weight to it that I really like is that they're from Mesopotamia. They're from that ancient area, of Persia and Babylon,
Mm-hmm.
and they have the collective work and memory of Daniel and Ezekiel, or not Ezekiel, of Daniel. Well, probably Ezekiel, but Daniel was there. Ezekiel, Shadrach, Meshach, Abednego, all, and Daniel trained a lot of their
Testing.
what they call
One,
seers, and
two, 1, 2.
that's a little better. Yeah.
Oh,
Um,
you can wait. You can hear me when I press mute. You can hear me. You can hear me.
you can hear you now. Yeah, we could hear you.
You're
I
not
wonder if
sure
you
if you would
switched
hear me.
mics.
Oh, okay. Oh, wait. Oh, so the mute. Wait, you were able to
There
hear me?
you go.
Oh, okay.
There you
Wait.
go.
Oh my goodness. The mute button on my microphone isn't working. So when I hit mute, the sound gets really low. Okay, got it. Got it.
Mhm.
Okay, thank.
Yep.
I'll figure it
Yeah.
out later.
So
Thank you.
yeah, Daniel helped train their astrologers coming up, the new wise men. Daniel and Ezekiel and Shadrach, Meshach, and Abednego would have been involved in training them, so they would have had this not only
Hmm.
Mediterranean or Mesopotamian wisdom, they would have had the Hebrew wisdom with it. So they would have put that together, and then they would have known when to show up when the incarnation begins. It's such a beautiful thing where you just see this carry and continuation.
Mm-hmm.
That knowledge was preserved in Babylon, even though Babylon has been
Yep.
problematic in history, but they also preserve that knowledge. So it's
Mm-hmm.
amazing to me.
Well, and notice how that fits with what I said about truth and meaning,
Hmm.
because these were people who said, I have no idea what that is, but I know what
Hmm.
it means,
Yep.
right? And today we know a lot about what something is and no idea what it means.
Hmm. Yeah, which is where that collective ancient wisdom comes in, because it gives you a mechanism to remember. Well, this would be, they would know this is a phenomenon in the stars. We don't know what it means. We know it's going to happen, and now we can predict that it's coming. So then they're there on their way when it happens, and then they show up. Takes them a couple of years to get there because of traveling and all that. But it's, yeah, this whole idea, and it also, I think, the stars give a, like I said, they paint that picture, and it's also going to remind people of, like, one of the beautiful narratives of the Old Testament is that now we've got um, this remembrance of how to endure suffering, and that carries through in this ancient story that, again, we've disconnected from, and now we've lost. And it's hard. I think suffering now is harder because we don't have that collective memory to help sustain us of how to suffer. So
Well, and suffering now is you're not part of a collective story. So
mhm,
your suffering now is just pain divorced from meaning.
yep.
And so there's no way to interpret it. There's no way to incorporate it. And
Hmm.
so, I mean, yeah, you're just suffering, and
Hmm.
it's that's just a terrible way to live.
Right. You hear so many people, why am I suffering? Why is this happening? But if you're suffering in a vacuum, you don't have that pool of thousands of years of how to endure it and how to give it meaning and how to understand the depth of it. So yeah, I mean, this is why I love being an Old Testament major, because you get to really dig into the foundation of a lot of this Christian tradition, and where the weight of the Christian tradition, it really is, reminds me of icebergs. Like, we only now see and experience the tip point, you know, poking up. But if you get into it, there is so much, like, what, 90% of an iceberg is underneath the water. And if you cut yourself off from the 90% underneath, no wonder people are feeling alone and isolated and disconnected, and people are, just don't know how to survive mentally and emotionally and spiritually anymore because we've cut off, so much there and so much was lost. But anyway, I don't want to get too deep down this road, but
Hey, that's what you do, right?
that's what I do.
I'm glad. No, I'm glad you guys getting in on the topics that you guys cover that you guys are versed in, and relating it.
Because there is ties, and I think that if we can learn to see how some of this mathy, sciencey, nerdy stuff connects to ancient tradition and wisdom, I think that not only brings communities together, but that shares and reconnects us to this collective memory and wisdom that we have all lost that real rhythm and connection to.
I think it can go a long way in getting people on the same page, because when you got like
Mhm,
meaning tied to this stuff, maybe people wouldn't be so flippant about dismissing particular elements. And I get that
mhm,
there's somebody's distrust with relation to the mainstream scientific community. I empathize with that a lot.
mhm,
Um, and like with the dark matter thing, there's very valid debate there, and somebody's like, it puts off alarm bells to people when you're not allowed to debate, or sometimes it's the opposite when someone's too incredulous about something. It's like, well,
mhm,
you got to have a reason for it, but still, I mean, if you have meaning tied to it, maybe that would strengthen the bond a little bit,
mhm,
and I'm sure there's gonna be some things that like contradict each other. That's something that is bound to happen, but I don't know. I'm seeing some like interesting things that like I could see things being categorized differently at the time that any given book like the book of Job was written,
mhm,
and that we could still correlate that to something that perhaps we can match up with today. And of course, just because people didn't realize that something was a triple star or whatever it was, like
mhm,
they see 3 stars, and that's what we see from the ground as well. So we can certainly relate to that and the meaning that they would have tied to that observation.
mhm.
And it doesn't really change the meaning just because I can show you a triple star in 2 out of 3 stars plus 5 stars over there. Like, it's still
Mhm.
the same 3 points of light from the ground, and the
Right.
calendar dates and all of that are all there.
Well, and it's going to be like that. Maybe that's why we could see it from this far away, because it was this collection of, multiples together that made it brighter. Like it,
Oh,
I don't see, like it's not always necessarily contradiction. And sometimes that you got to step back and look at the bigger thematic and narrative of both science and tradition together, because that's one of the things that I've been trained to do is step back and look at the bigger narrative, not get focused on the details, but weigh the details in concert of or in perspective of the bigger narrative. So, I think there's a lot of missed conversations that could be happening with that
I,
perspective.
I think we had a great example of that when we were looking at the
Mhm,
stars, that from the vantage point we were at, we
mhm,
saw one point, but then Ronnie, when you were hovering over it, it's
mhm,
like, well, no, I don't want the combined mass. Wait, combined mass. And so it's not a contradiction, it's different
mhm,
levels of resolution. So you can
mm-hmm.
have a
Yeah.
resolution of truth. And then if you magnify that and get down super particular, where you lose the large broad scope, but you want to get
yeah.
super granular on something, you can have more detail added. That doesn't affect the lower levels of resolution, which are what provide you with greater levels of coherence.
Mhm.
Well
And
said.
I
Yeah.
think I think we've also forgotten that science was born out of a curiosity to engage with God's world.
Mm-hmm.
And now I think there's been such a breakdown in the encouragement of curiosity that it has moved so left brained, purely logical on the science side, that it is harder to engage in the faith side with the lack of curiosity. And so I think getting back to curiosity and storytelling and understanding, things in balance that way. And the religious side needs to get better at not being afraid of answering questions either, because it's sometimes the fear of I don't know or lack of perspective, like you were talking about, Shaun, that really shuts down the conversation from our side. And that needs to change as well.
And I think that this idea of having this broad, rich tradition to pull on, this provides us with hooks on which to hang new things that we
Mhm.
find.
Mhm.
Whereas, unfortunately, what we have going on in the very superficial Christian traditions is they're afraid of this stuff because of the fact that they've dismissed their tradition. They're
Mhm.
basically operating from, we created our narrative out of the evidence that we had, and we can't get new evidence because that will now challenge the narrative and we have to
Mhm.
restructure. Whereas if you have this broad, deep well that you're pulling from, you have all these hooks that you can hang things on. Like, great, we find more stuff. That's so
Mhm.
awesome. Let's
Yeah.
find ways to incorporate it, and then you just change. Maybe like we saw. Okay, well, there's double stars here. Oh my goodness, there's a double star within that one. That's so cool. And it's like, yeah, we can totally accommodate all these things because we're
Mhm.
not stuck on one level of resolution.
Mhm. Yeah, it's just about broadening out and giving yourself like re-anchoring to that depth. And that's just one of the things that I love so much that Old Testament studies helps us do is to anchor and give more hooks and anchors to things from perspectives where you're looking at poetry in the Psalms and it's talking about the majesty of the stars and all of these other things, and you can be like, okay, this is painting a picture for some of the scientific phenomenon that now we can see scientifically and mathematically measure and use programs like Ronnie was showing us to rotate around, and so it isn't debunking like the book of Psalms. It's just bringing all of this. To me, it just makes it even cooler because it's like, look at what poetically they saw back before they could technology they could never imagine, and they were able to look up and poetically express what we were going to get to see with our eyes. And that to me is just like, isn't this amazing? Like, like I don't have to be afraid of debunking anything because it's already painted as a beautiful poetry that's not scientific, but it's the right brain expression of the left brain that was coming. So they work together, and that's the beautiful thing. All right, so we are hitting the 3 hours. It's been a long, very cool episode, but this is about the I think the limit of, of time
Well,
that we
I
can
just want to
make it
quote
go.
Roddy K
So
by saying, "Living
okay.
living is easy with."
Mhm.
Okay, let me say that in English. Living is easy with eyes closed, misunderstanding all you see. The Beatles. Oh, I thought it was a Bible verse. Okay, go on. I thought it was being a Bible verse just now, and I'm
That's
seeing the
exactly
Beatles.
what
I'm like,
it is. No.
the Book of Beatles. Which one is that?
Nope. We quote all kinds of weird stuff around here.
But
That's
I don't.
right.
I
So,
don't
all
disagree though.
right. Yeah. Yeah, let's do like your one final takeaway thought to wrap up. So, Sean.
My final takeaway thought would be that this is just awesome. I love getting to nerd out with this stuff with Ronnie. And I could listen to him all day because he goes into these topics. He ends up discovering a curiosity and delves deeper into that. And that's
Mhm.
exactly the way my brain works. I can see you clicking the hyperlinks on your curiosity in your brain, and I'm like, dude, that's awesome. That's exactly how I think. So I love that. But I think that what we're doing here is just showing the majesty of God's creation, and
Mhm.
um, nothing that we see here scares us. We love it. We love it, and we love what God has for us. So I think it's unfortunate when people are afraid. Um, I think it just shuts down conversation,
Mhm.
and I think that we shouldn't be afraid. And I think that's part of what me and Amber were just talking about is if we have a deep well to pull from, um, fear goes away, right? You're
Yeah.
part of a story. You're part of a narrative, and you're not the center of your own story. You're just another piece in this chronology. So I think that that's really important for us to find in today's day and age where everyone is so um, to borrow a word from Josh Davidson, disintegrated, right? There's
Mhm.
so much disintegration going on. We're not integrating anymore because we see ourselves as the center of our own story. You don't have your own gravitational field. you're in somebody else's gravitational field. um,
Mhm.
and even though there is that correlation of you're important and maybe you manipulate the center in such an extent that um, you do have mass, uh, you are orbiting something bigger than you. um, and so I think that these conversations are super important. And I really love the opportunity that I've had here to be able to just be a witness to what Ronnie was able to show us and communicate to us.
It's amazing. All right, Ronnie, what's your last thought takeaway from all this?
3 hours later. Dot dot dot. That's my final thought, and I'll work on that because I definitely want to give people shorter answers that get to the point. But sometimes it's important to me to kind of get that foundational
Mhm.
knowledge out, so that when I'm sharing something, I hopefully give enough background that my rationale is explained. But at the same time, my coworker who sometimes has weird conspiracy theories, he brings up a good point about certain things. Like, he doesn't accuse this of me, luckily, but if somebody gives you too long of an answer, that could be a sign that they don't know what they're talking about. Sometimes it's like,
Mhm.
if you can give the answer in fewer words, you know what you're talking about. But I'll endeavor to do that, and I'm just glad that I was able to share this with you guys. I had a lot of fun. I appreciate your questions. I don't think I delved deeply into the Butterfly Nebula. I'll do that on my next show. I'll probably do that next week. I think we should talk about the Butterfly Nebula. But in short, it looked like it was one of those it looked like it was a bunch of ejection of matter. In fact, let's briefly
Mm.
give a final thought on the Butterfly Nebula, if that's okay with you. I'm not gonna delve. We're not gonna do questions. We're just gonna take a quick look at it because
Right.
I didn't even touch it. I apologize. So, bottom line, it structures a nebula among the most complex ever seen planetary nebula. Planetary nebulae are not necessarily made from planets, but anyway, the structure is among the most complex. Oh, come on! I don't, just tell me to punch. The central star, a white dwarf, was identified in 2009 using upgraded wide field camera through on the Hubble Space Telescope. The star has a current mass of around zero point 0.6, about half the size of the sun. It is surrounded by a dense equatorial disk compound of gas and dust. So, gas and dust. This
Mm.
dense disk is postulated to have caused the star's outflow to form a bipolar structure similar to an hourglass. The bipolar structure shows features such as ionization walls,
Mhm.
knots, and sharp edges. So bottom line is, when they say ionization walls, that red or yellow, it's like when I did that
Wow.
hydrogen filter. It tuned into a very particular
Uh-huh.
shade of ruby red. And so, yeah, I'll touch on that on my show more. But some of this is a bit amped up due to long exposure photography. But bottom line is, you got a little white dwarf star in there. You got a disk of matter there, and I guess the stellar wind or something is pushing it outward, and I'm gonna just refrain from explaining more without doing my homework on that. But that is all, and those are my final thoughts. Thank you, Amber.
Sure thing. So I guess my final that just kind of changed my final thought a little bit there
I'm
too, because I'm just it's okay. Because I love so I'll go back to my original final thought and just kind of stew on what you just said there because that there's some language there and I want to think about that and maybe Sean and I can back and forth on that and we'll come up with a
yeah.
plan for another episode because that would be amazing with that but it's not a thought that's ready yet. So my thought is this that when we are connected in relationship to um, our our Trinity and a Trinitarian relationship, that is a relationship that is an expression of the Hebrew word hesed, which is so much bigger than just love. It is long suffering. It is mercy. It is loving care. It's a very beautiful, complex word. But in that is the source of curiosity because if you're not in a place of love, it is almost impossible to be curious. And so, in relationship with a loving God, curiosity should not only be there, it should be encouraged, it should be nourished because that is going to be one of the biggest bridges to people and between people is curiosity. It's my curiosity about Shaun that has gotten us to become good friends. It's been my curiosity with watching Ronnie's channel and stars and planets and just having fun chatting with him. They could just love sparks curiosity, and that's something that has to come, I think, from the weight of being connected to something bigger outside of ourselves we only have so much internal curiosity, but we can tap into an infinite source of curiosity. And that is something we have very sadly lost and discouraged in so many, especially in our children. And that needs to change to foster that sense of curiosity once again. So that's my last thought. So, Ronnie, what have you got coming up on your channel? I think it's linked in the description. I'll double check after we're done and make sure it's down there. But what do you have coming up now besides the Butterfly Nebula?
Well, the good news is I don't have to do my Monday show on Thursday because it's already 10:45, so I'm off the hook. Woohoo! No, I'm kidding. I had a blast. And I almost forgot that like I had a show on the same day. I usually would do it on a Wednesday, but yeah. So next Thursday around 10:45 p.m. I will continue my regularly scheduled programming with the Monday show on Thursday. That's to avoid confusion. But anyway, and last week I covered a movie called Letters from Iwo Jima. It's a Clint Eastwood film. He directed it, and it's cool because what he did was he directed two films about Iwo Jima, one of the major, island battles of World War II. And Letters from Iwo Jima is from the Japanese perspective, and Flags of Our Fathers is from the American perspective. So you got like
Mm.
two movies where he was able to recycle the props for both movies, so he saved money. No, but all jokes aside, it's cool because you
Right.
get like you do get like because I do enjoy learning about that from the Japanese perspective, and not just from like the upper echelon war criminals, but like from the average soldier and from the people who were literally just like generals and commanders just doing their job who really were not up to anything bad aside from being engaged in war, which is like a crime on every side of the war, so to speak. But very, just interesting movie based on some real letters and things like that, and firsthand sources and interviews with people who were there. Beautifully, masterfully done directing. So I reviewed that last week. Next week, I might review the counterpart film if I get it in time, which is Flag of Our Fathers. And if I don't, I might have another movie to review, or maybe we'll just go and do some space stuff. You never know. If the weather is good, which the weather has not been good lately, we can do some astrophotography. But you can never predict the weather unless a week out. So we'll just play it by
Right.
ear. But yeah, I will be back next Thursday at 10:45 p.m. Eastern time on my channel.
All right, Shaun, for people who want to know more about you and where they can find you, where are you and what have you got coming up?
Tomorrow on Myths, Mysteries, and Majesty, Nico and I are doing the Amityville Horror. So we're going to be looking into the things that happened. We're going to be looking into the evidence that Ed and Lorraine Warren were able to gather, and it's going to be a blast. And then next Friday, I'll be on Faith Unaltered's Cosmic Corner, and we'll be having a conversation. Uh-oh.
I was invited to come to that, and I'm not
Are
sure
you
if I can
coming?
make it. I might.
Oh,
I'm not sure. I don't.
that
Oh,
that would be awesome. We're going to be having a conversation about the cross. So
I know.
and it'll be on Good Friday. You can't get better than that. So if you're a follower of Faith and Altered, which you should be because Amber works with Faith and Altered, um, you should tune in to our Cosmic Corner episode. It's going to be at least Josh Davidson, Jalen, myself, and now maybe Amber if she wants to be involved in that awesome conversation. So yeah, that's where you can find me.
Yeah. So what? Yeah. So for me, oh,
Oh,
good
no.
grief. I've got we're gearing up for the most intensive 2 weeks of school here. So I'm grinding out the last end of the semester. So my channel's going on hiatus for the next couple weeks. I think tomorrow is an open mic night on Faith Unaltered, so I will be doing that. And I don't know about any of the Faith Unaltered stuff because I was asked to do that on Friday, and then there was something else that I think was happening. I'm not sure, but everything right now is kind of on because next week is Holy Week and there's a lot going on. My church has got a lot of stuff going on next week for that and school and with all that stuff. So we shall see. I may or may not be on. Joe Davidson reached out and he was like, "Hey, it would be awesome if you could come." And I'm like, "Well, we'll see." I can't say yes, but I don't want to say no. So we'll see. Because especially if Sean's coming, then I'm just like, dang, I gotta come hang out with Sean because that's always fun. So, but yeah, but we're going to be resuming the Torah series. Is going to be picking back up. Um, why Leviticus matters. We're going to be picking that back up, getting that going up, and finishing that up. And then that'll take us into the summer where we on my channel I am going to go through the apocrypha and the pseudepigrapha, and we're going to talk about what's in there, because I think that there's a lot that's lost where people just immediately dismiss it and discount it, because you don't have to include it in the 66 book canon. I'm not saying we're going to put it in there. I'm just saying that we should know what's in there and interact with it, because there's a lot of tradition and there's a lot of things that the New Testament writers would have been familiar with and reference that material, and would have been stories that they were thinking of when they were writing a lot of the New Testament. So we at least need to know what's in it, in the Apocrypha. So we're going to go, because there's some, let me tell you, if you like war elephants, this is the stuff for you, because there's war elephants in there, and there's like weird Tobit. We don't, Tobit's going to be fun, because there's weird stuff in Tobit too. So it's going to be, I think, a really fun series throughout the summer. And then I also have working on planning a look at Ezekiel and Daniel, because I think they're very misunderstood books. And so we're going to talk about, and I might just rope Sean into some of that, some of that conversation, because there's some weird stuff in there too. So we love the weird stuff around here, as it's the fun stuff to talk about, the stuff that nobody wants to talk about because it's weird. I love to talk about that stuff. So, all righty, everybody, Shaun and Ronnie, thank you so much. This was fantastic. I had a blast, and we will definitely do this again, because it's just so much fun, and getting Ronnie to come and show us all this really cool stuff. I absolutely love it. So thank you a lot, guys. Thank you, everybody, for people who are coming in and out and saw the chat interacting. And it was just really glad that you all were here. Please like this. If you haven't subscribe to my channel, go to 3M and go check out Sean and Nico over there. Go over to check out Ronnie's channel. If you haven't subscribed to them, go subscribe to their channels. That's just, that's what we do around here. We encourage and promote each other, because that's what we're all about. So everyone, have a great coming up weekend. We're getting ready for Holy Week. We're getting ready to celebrate the Christian New Year and the Christian reason that everything exists. And so go with God and be blessed.